July 1st, 2025. A computer in Hawaii flags something that shouldn't exist. An object beyond Jupiter's orbit, 5 times farther from the Sun than Earth is, glowing bright enough to be spotted easily. Not just a faint smudge. Bright, unmistakable. And here's why that matters at that distance. You're in the deep freeze of space where temperatures hover around minus 230 degrees Celsius. Comets out there are frozen solid, inactive, just chunks of ice and rock waiting for the sun's warmth. They don't develop their characteristic glow, that cloud of gas and dust astronomers call a coma, until they get much closer. Usually inside 5 astronomical units, inside Mars's orbit. That's not a guess, that's observed physics. We've watched hundreds of comets, and they all follow the same pattern. The ice needs solar radiation intense enough to sublimate, turn directly from solid to gas, and create the pressure that makes them visible. Atlas was glowing at 5.2 astronomical units. Farther out than it should, Avi Loeb, Harvard's chair of astronomy, looked at the brightness data and did what any physicist would do, worked backward. If you know how bright something appears and you estimate its reflectivity, what astronomers call albedo, you can calculate its size. The number kept coming back 20 kilometers in diameter. Let me give you a sense of scale here. Manhattan Island is about 20 kilometers long. The asteroid that ended the dinosaurs 66 million years ago was roughly 10 kilometers across. This thing, if the initial estimate was right, was double the dinosaur killer. And that's where Loeb's statistical alarm bells started ringing. He later wrote, "Given the limited reservoir of heavy elements in interstellar space, we should have discovered on the order of 100,000 interstellar objects on the scale of Oumuamua before finding Atlas." 100,000. Here's why. The galaxy contains a certain amount of rocky material, carbon, silicon, iron, oxygen, all the stuff that makes planets and asteroids. Most of it's locked up in stars and planets. Some drifts in interstellar space as dust and debris, occasionally getting ejected from star systems during planet formation. When you calculate the density of that material, how many tons of rock per cubic light year, and you run the probability of objects crossing our solar system, you get what's called a power law distribution. Think of it like earthquake magnitudes or city populations. For every magnitude 7 earthquake, there are 10 magnitude 6 earthquakes, 100 magnitude 5s, 1000 magnitude 4s. Big events are exponentially rarer than small ones. Same with space rocks. For every boulder, there are thousands of pebbles. For every mountain-sized object like Atlas, there should be hundreds of thousands of Oumuamua-sized visitors. Loeb calculated that we should see an object Atlas's size about once every 10,000 years. We've been systematically looking for a decade. Those are the odds of walking into a casino, watching someone roll double sixes, and having it happen on your first visit. Could it happen technically? But you'd probably want to examine those dice pretty carefully. Now here's the thing. We'd already found 2 interstellar objects before Atlas showed up. Oumuamua in 2017, the one that made headlines worldwide. Borisov in 2019, both small, maybe 100 meters across. Football field sized, exactly what the statistics predicted we'd find first. So why did we find the giant before we found the expected thousands of small ones? You've got 3 possibilities. 1, our telescopes are terrible at spotting small objects, and we're missing literally hundreds of thousands of them. 2, Atlas isn't actually 20 kilometers across, and that initial brightness calculation was wrong. 3, something about Atlas is producing light in a way that has nothing to do with reflected sunlight. Loeb kept circling back to option 3. Not because it's exotic, because the other explanations weren't adding up. Standard comet behavior says you need to be within 5 astronomical units before the sun's radiation is strong enough to sublimate ice and create visible outgassing. That's a temperature threshold. a physics boundary we've observed over and over. Atlas crossed it early. As Loeb put it in one interview, it was like watching a streetlight turn on in the middle of the Antarctic. Shouldn't be doing that yet. So either comets can activate earlier than we thought, which, fine, science changes, or something else was generating that glow. Internal heat, maybe. Some kind of power source that doesn't require external solar radiation. And that's the first whisper of the hypothesis that's going to make a lot of scientists very uncomfortable. But Loeb isn't leading with aliens, he's leading with anomalies. Plural, because the brightness was just the opening act. By late July, astronomers had tracked Atlas long enough to calculate its trajectory. And that's when the second anomaly showed up. Interstellar objects entering our solar system can come from literally any direction. The galaxy doesn't have a preferred orientation. There's no cosmic highway all the traffic follows. An object from another star system should arrive at a random angle, completely unrelated to the flat plane our planets orbit in the ecliptic. Atlas doesn't do that. Its trajectory is aligned with the ecliptic plane to within 5 degrees. Nearly flat, almost perfectly in sync with Earth. Mars, Venus, Jupiter, the whole inner solar system. Loeb ran the math. Random probability of that alignment 1 in 500. Not impossible, just notable. Eyebrow raising, but then you add the planetary encounters, and notable becomes deeply strange. Atlas doesn't just pass through our solar system on a flat trajectory. It passes close to 3 planets, Mars, Venus, and Jupiter. Not just anywhere in their orbits, it arrives when they're actually there. Think about what that requires. Mars takes 687 days to orbit the Sun. Venus takes 225. Jupiter takes 12 years. They're all moving at different speeds, in different positions, constantly. For an interstellar visitor to thread the needle and pass near all 3 during a single flyby, the timing has to line up with absurd precision. On October 3rd, just days from now, Atlas will pass within 29 million kilometres of Mars. In cosmic terms, that's a near miss. Close enough that NASA's already repositioned the Mars Reconnaissance Orbiter to image it with HiRISE, a camera designed to photograph individual boulders on the Martian surface from orbit. That image is going to separate the nucleus from the surrounding dust cloud for the first time. We'll finally see what Atlas actually looks like at its core. And it's not just Mars. Venus gets a relatively close flyby. Jupiter too. All 3 planets, all during the same pass through the inner solar system. Loeb calculated the combined odds of a random trajectory hitting those marks 1 in 20,000. We're not talking about one lucky break anymore. We're stacking them. The brightness anomaly, the size, the ecliptic alignment, 3 planetary close approaches with perfect timing. Individually, each one could be coincidence. But together, Loeb uses this line that I think captures it perfectly. You can argue that each individual thing is just a coincidence. But at some point, when you keep rolling 6s over and over again, you have to start wondering if the dice are loaded. And then there's the perihelion date. The moment Atlas reaches its closest point to the Sun, October 29th. On that specific date, Earth will be on the exact opposite side of the Sun. Atlas will be in what's called solar conjunction, the Sun directly between us and the object. Every ground-based telescope will be blind. Even space telescopes struggle because the Sun's glare drowns out everything nearby. We won't be able to see it. And Loeb looks at that timing and says something that makes my skin prickle. This could be intentional. If you wanted to make a major course correction without being observed, this would be the moment. The Sun's gravity is strongest at perihelion. Velocity is highest. It's the optimal point for what's called an Oberth maneuver using orbital mechanics to amplify thrust. Normally, we use the Oberth effect to speed up. Every deep space probe we've launched, Pioneer, Voyager, New Horizons fires engines at perihelion because that's when a little bit of fuel gives you the biggest velocity change. But it works in reverse too. You can fire engines to slow down, to bleed off speed, to let the sun's gravity capture you into a bound orbit instead of letting you escape back into interstellar space. If Atlas makes that maneuver on October 29th while we can't observe it, it could transition from just passing through to staying permanently. Not a visitor, a resident. We won't know until late November, maybe early December, when Atlas re-emerges from behind the sun and we recalculate its trajectory. If the orbit has changed, if it's no longer on an escape path, we'll know something happened during that blackout window, but we won't know what. We won't see the maneuver. We'll only see the before and after. And that observational gap at the single most critical moment in the entire encounter, that's what keeps Lobe up at night. Because here's the fundamental problem with science: we trust what we can measure. But when you can't measure the thing that matters most, you're left with inference, guesswork, probabilities instead of certainties. So let me lay out where we are right now, in early October 2025, an object that's too bright for its distance, possibly too massive for the statistical distribution, on a trajectory aligned with our planetary plane with 1 in 500 odds, passing near 3 planets with 1 in 20,000 timing, arriving at perihelion on the exact date when Earth can't observe it. Coincidence? Maybe. Probably, even. But as Lobe keeps pointing out, and as we're about to see, the brightness and trajectory were just the first layer. Because when astronomers started measuring not just where Atlas was going, but what it was made of and how it was moving, the contradictions started piling up faster than the explanations could account for them. Here's what happened last week that changed everything. Loeb's team compiled data from 227 observatories around the world, over 4,000 individual observations, months of tracking Atlas's position with absurd precision. And they weren't just measuring where it was, they were measuring where it should be if gravity were the only force acting on it. Because here's the thing about comets: they don't move in perfect gravitational arcs. They cheat. When a comet gets close to the sun and starts heating up, ice on its surface sublimates, turns directly from solid to gas without becoming liquid first. That gas jets off into space. And when gas jets off one side of a comet, it acts like a tiny rocket engine. Astronomers call this non-gravitational acceleration. It's one of the defining signatures of an active comet. You can measure it by tracking the object over time and comparing its actual position to where pure gravity would put it. If it's ahead or behind by a little bit, that tells you the outgassing is pushing it around. Every active comet we've ever studied shows this. It's physics. Gas equals thrust equals deviation from a purely gravitational path. Atlas shows almost none of it. The upper limit on its non-gravitational acceleration is less than 15 meters per day squared. That's tiny. That's way smaller than what you'd expect from a comet that's clearly outgassing. And we know Atlas is outgassing. The James Webb Space Telescope observed it on August 6th and measured the gas coming off its surface. The mass loss rate is about 150 kilograms per second. 150 kilograms every second. That's a small car's worth of material being thrown into space continuously. That much gas should be pushing Atlas around. Noticeably, measurably, but it's not. Loeb looked at that contradiction and asked the obvious question why, and the math gives you a very specific answer. If Atlas is heavy enough, if it weighs enough, then the thrust from outgassing won't move it much. It's like trying to push a cruise ship with a leaf blower. The force is there, but the mass is so large that the acceleration is negligible, so they calculated it. Given the observed outgassing rate of 150 kilograms per s and the absence of detectable non-gravitational acceleration, What's the minimum mass Atlas could have 33 billion tons? That's not an estimate with error bars the size of continents. That's a lower bound. Atlas has to weigh at least that much, or we'd see it getting pushed around by its own gas jets. 33 billion tons minimum. Now, if you assume Atlas is made of rock and ice with a density similar to other comets, roughly 500 to 1,000 kilograms per cubic meter, kind of like loose gravel, you can work backward and calculate a minimum diameter. It comes out to more than 5 kilometers. Possibly significantly more, depending on how dense it actually is. So we're back to a big object. Not the initial 20-kilometer estimate, but definitely on the large end. Definitely more massive than any other interstellar object we've seen. Loeb points out in his latest paper that this makes Atlas 3 to 5 orders of magnitude more massive than Oumuamua or Borisov. 3 to 5 orders of magnitude. That's a factor of 1,000 to 100,000 times heavier. And that brings us right back to the original statistical problem, the power law distribution problem, the why did we find the mountain before we found the thousands of pebbles problem, except now it's worse. Because 33 billion tons isn't just heavy for an interstellar visitor, it's heavy in a way that creates a paradox. Let me walk you through this because it's where the math starts to feel like it's breaking. Space debris follows a pattern. For every big object, there are exponentially more small objects. We see this everywhere: asteroid belts, planetary rings, comet populations. It's as fundamental as gravity. If you plot the number of objects versus their size on a log scale, you get a straight line sloping down. Big objects are rare, small objects are common. The slope of that line tells you the distribution ratio. For our solar system's asteroid belt, for every asteroid that's 10 kilometers across, there are roughly 1,000 that are 1 kilometer across, and 1,000,000 that are 100 meters across. The distribution is steep. Size matters exponentially. Now, apply that same pattern to interstellar objects. Based on planet formation models and observations of debris disks around other stars, we can estimate how much material gets ejected into interstellar space and what size distribution it should have. The calculation Lobe keeps coming back to is this: if Atlas represents the large end of the distribution, where are all the small objects that should exist in vastly greater numbers? The Vera Rubin Observatory just came online this year. It's finding asteroids in our solar system at an incredible rate, thousands per week. It's designed to spot faint, fast-moving objects. If interstellar visitors were common, if there were hundreds of thousands of Oumuamua-sized rocks passing through regularly, Rubin should be drowning in detections. It's not. Since it started operations in early 2025, it's found maybe a handful of candidates, most still being confirmed. So you've got two options. Either the mass budget for interstellar debris is way higher than we think, there's just tons more material out there than our models predict, or Atlas is anomalously massive for reasons that have nothing to do with natural distribution. And here's where Loeb's hypothesis starts to sound less crazy. What if Atlas isn't a solid rock? What if it's hollow? Think about how we build spacecraft. The International Space Station is huge, over 100 meters across, but it doesn't weigh much relative to its size. It's mostly empty space with thin walls. If you saw it from the distance and assumed it was a solid chunk of metal, you'd wildly overestimate its mass. But measure how it responds to thrust, and you'd realize it's much lighter than a solid object that size should be. Same principle could apply to Atlas. A hollow structure with a diameter of 10 or 15 or even 20 kilometers could easily weigh 33 billion tons if the shell were thick enough, and it would look from the outside like a giant solid object. It would reflect sunlight like a big rock, but it wouldn't behave like a big rock when you measured its mass. Loeb doesn't say this explicitly in the interview. He dances around it. He talks about how we shouldn't judge a book by its cover, how the chemical composition we're detecting on Atlas's surface, the CO2 and water ice, could just be material that collected on its exterior as it travelled through interstellar space. Frost on the windshield, basically. But the implication hangs there. If you're open to the idea that Atlas might be technological, then 33 billion tons suddenly becomes less of an anomaly and more of a data point. It's heavy, but not as heavy as a solid rock that size would be. It's massive enough to resist perturbations from outgassing, but light enough that you could imagine it being constructed rather than formed naturally. Now, before you think I'm going full Ancient Aliens here, let me be clear about what Loeb is actually arguing. He's not saying Atlas is definitely a spacecraft. He's saying the data we have doesn't rule it out. And in science, that distinction matters enormously. The natural explanation is still the most likely Atlas is a comet from another star system. Unusual one. Certainly. Heavier than expected. Brighter than it should be at that distance. With a trajectory that's statistically unlikely but not impossible. But the technological explanation isn't absurd. It's not pseudoscience. It's a hypothesis that fits the observations, and until we gather better data that definitively excludes it, it deserves to be on the table. Here's the key insight Loeb keeps hammering on: the absence of non-gravitational acceleration, combined with confirmed outgassing, requires Atlas to be massive. That's not speculation, that's physics. 33 billion tons minimum. No way around it. And finding an object that massive this early in our survey of interstellar visitors violates every statistical expectation we have. So either we've been extraordinarily lucky winning the cosmic lottery on our first handful of tickets, or something about Atlas doesn't fit the natural distribution model. Loeb uses this gambling analogy that I think crystallizes the whole argument. If you walk into a casino and see someone roll double sixes 10 times in a row, the odds are about 1 in 60 million. Could it happen? Technically, yes. But you'd probably want to take a closer look at the dice. That's all he's asking for. Take a closer look at the dice. The 33 billion ton mass, stacked on top of the brightness anomaly, stacked on top of the trajectory alignment, stacked on top of the planetary encounter timing, each one individually might be explainable as random chance. But together, they paint a picture of an object that keeps defying expectations. And we haven't even gotten to the chemistry yet. We haven't talked about what Atlas is actually made of, or why it started glowing green at the exact moment spectroscopy said it shouldn't, or what happened when Hubble first imaged it and saw something pointing the wrong direction. Because if 33 billion tons is the mass problem, what we're about to discuss is the composition problem, and somehow it makes even less sense. Let's talk about the trajectory, because this is where coincidence starts to feel like choreography. When Atlas was first discovered, astronomers did what they always do: they calculated its orbit backward and forward. Where did it come from? Where's it going? And more importantly, what's good to run? What path is it taking through our solar system right now? The data gave them an answer that should have been unremarkable. Interstellar objects can approach from any direction in three-dimensional space. There's no cosmic traffic pattern they're supposed to follow. The galaxy doesn't have lanes. An object from another star system should arrive at a random angle, completely unrelated to the flat plane our planets orbit in what astronomers call the ecliptic. But Atlas's orbital inclination 5 degrees. 5 degrees off the ecliptic plane. To put that in perspective, Earth orbits at 0 degrees by definition. That's what defines the plane. Mars is about 1.85 degrees. Venus is 3.4 degrees. Jupiter is 1. 3 degrees. Atlas, coming from interstellar space, from a star system with its own geometry and orientation, arrives aligned with our planetary plane almost as precisely as the planets that formed here. The random probability of that Lobe calculated it at 1 in 500. Now, 1 in 500 isn't impossible. It's not even that rare if you're looking at a large enough sample. Flip a coin 500 times, you'll get some unlikely sequences, but we're not looking at 500 interstellar visitors. We're looking at the third one we've ever detected, and it's aligned, but orbital inclination is just one parameter. There are 5 others that define a trajectory through space eccentricity, semi-major axis, longitude of ascending node, argument of perihelion, and mean anomaly at epoch. 6 numbers that completely describe how an object moves. For a truly random interstellar visitor, those 6 numbers should have no relationship whatsoever to our solar system's architecture. They're independent variables drawn from the cosmic equivalent of a random number generator. Atlas doesn't look random. Its trajectory doesn't just lie near the ecliptic plane, it's positioned such that it passes close to multiple planets during a single flyby. And not just spatially close, temporally close. It arrives when they're actually there. Think about what that requires for a moment. Imagine throwing a dart at a spinning dartboard from across a dark room. Now imagine the dartboard has multiple targets rotating at different speeds, and you need to hit 3 of them with one throw. Not just hit the board, hit the specific spots where those targets happen to be at the exact moment your dart arrives. That's what Atlas's trajectory does. October 3rd, and this is happening in just days, Atlas will pass within 29 million kilometers of Mars. In astronomical terms, that's intimate. That's close enough that NASA's already repositioned assets to observe it. The Mars Reconnaissance Orbiter, which normally photographs the Martian surface, will turn its HiRISE camera toward Atlas. HiRISA has a resolution good enough to see individual boulders on Mars from orbit, pointed at Atlas from 29 million kilometers away. It should resolve features down to about 30 kilometers. That's not enough to see surface details, but it's enough to separate the nucleus from the surrounding coma and get a real-size measurement. Not an estimate based on brightness, an actual image-based measurement. And here's what makes the Mars encounter particularly interesting: the minimum orbit intersection distance the closest Atlas's trajectory gets to Mars's entire orbital path is only 2.7 million kilometers. 2.7 million kilometers. If Atlas had arrived just slightly earlier or later, if its speed were different by even a fraction of a percent, it could have come even closer. The trajectory threads a needle that's absurdly narrow given the scale of the solar system. But it's not just Mars. Atlas also makes a relatively close approach to Venus. Not as close as Mars, but still well within what astronomers would call a significant encounter. And farther out, near Jupiter's orbit, there's another near pass, though at a greater distance because Jupiter is so much farther from the Sun. 3 planets, 3 encounters, all during a single pass through the inner solar system. Lobe ran the math on the combined probability. He looked at Atlas's trajectory and asked what are the odds that a random interstellar visitor would pass this close to Jupiter's orbit, Mars's orbit, and Venus's orbit at the times when those planets are actually in those positions. Because remember, the planets are moving. Mars takes 687 days to complete one orbit. Venus takes 225 days. Jupiter takes 12 years. They're constantly in motion, constantly shifting position. For Atlas to arrive with timing that puts it near all 3 during its flyby, the synchronization has to be extraordinarily precise. The answer Lobe got 1 in 20,000. 1 in 20,000. Now we're stacking probabilities. The ecliptic alignment was 1 in 500. The 3-planet encounter timing is 1 in 20,000. And we haven't even factored in the mass anomaly or the brightness problem yet, each one alone. You could shrug it off. Statistical flukes happen. But when you multiply these probabilities together, when you combine all the unlikely things that would have to be true simultaneously for this to be purely random, the numbers get uncomfortable. It's like that casino analogy Lobe uses. 1 double 6 roll? Sure. 2 in a row? Okay, lucky. 3, you're starting to pay attention. But 10 times in a row, at some point, you stop calculating the odds of coincidence and start asking if there's a pattern. And then there's the perihelion timing, which is where this whole trajectory analysis gets deeply strange. Atlas reaches its closest point to the Sun on October 29th. That's perihelion, the moment when it's moving fastest, when the Sun's gravity is strongest, when orbital mechanics matters most. If you wanted to make a major course correction, perihelion is when you do it. That's when a small change in velocity produces the biggest change in your final trajectory. It's called the oerth effect, and it's fundamental to spaceflight. Every deep space mission we've ever launched uses this principle. When Voyager flew past Jupiter, it fired its engines at closest approach, because that's when the fuel efficiency was highest. When New Horizons boosted toward Pluto, it timed the burn for perihelion around Jupiter. You get more bang for your buck when you're moving fast near a massive object. Now here's the thing about Atlas's perihelion. On October 29th, Earth will be on the exact opposite side of the Sun. We'll be in what's called solar conjunction. The Sun will be directly between us and Atlas, and the glare will make observation impossible. Ground-based telescopes will see nothing. Space telescopes like Hubble and Webb will struggle because anything that close to the Sun's visual position gets drowned out by scattered light. We won't be able to watch what happens. Loeb looks at that and asks a question that makes a lot of his colleagues very uncomfortable. Is that intentional? If you were designing a trajectory that allowed you to make a course correction without being observed by the most technologically advanced planet in the system, this would be it. You'd arrive at perihelion where maneuvers are most efficient at the exact moment when that planet can't see you. It's not just convenient, it's optimal. Now, let's be very clear about what Loeb is and isn't claiming here. He's not saying Atlas is definitely going to make a maneuver on October 29th. He's not saying it's definitely a spacecraft. He's saying the setup is suspicious, the timing is too good, and we should be paying very close attention to what happens when Atlas re-emerges from behind the Sun in late November. Because if the trajectory is changed, if Atlas comes out on a different orbit than it went in on, we'll know something happened during that blackout window. We just won't know what. The most significant possibility is orbital capture. Right now, Atlas is on a hyperbolic trajectory. That means it's moving faster than escape velocity. It's going to swing around the Sun and head back out into interstellar space unless something changes. But if Atlas were to slow down at perihelion, if it were to use some form of propulsion to bleed off velocity, the Sun's gravity could capture it into a bound orbit. Instead of passing through and leaving, it would stay permanently. It would become a resident of our solar system. Loeb calls this a reverse oerth maneuver. Instead of speeding up, you slow down. Instead of escaping, you get captured, and the physics works exactly the same. You get maximum efficiency by making the maneuver at perihelion when you're moving fastest. The velocity change required wouldn't even be that large. Loeb estimates that slowing down by just a few kilometers per second at perihelion would be enough to transition from an escape trajectory to an elliptical orbit. A few kilometers per second, that's within the range of chemical rockets. Well, within the range of anything more advanced. And if Atlas does that while hidden behind the Sun, we won't see it happen. We'll only see the result when we recalculate the orbit in December. Now, you might be thinking, okay, but there's no evidence Atlas has propulsion. We haven't seen any engine burns. We haven't detected any exhaust plumes or heat signatures. And you'd be right. We haven't. But here's the question Loeb keeps asking: what would advanced propulsion look like if you're a civilization capable of building interstellar probes which requires technology far beyond anything we have? You're probably not using chemical rockets that belch fire and smoke. You're using something more efficient, Ion drives maybe, magnetic sails, photon propulsion, technologies we haven't even conceived of yet. And those systems might not produce obvious signatures. No bright exhaust. No waste heat that stands out against solar heating. Just subtle, controlled thrust that's nearly impossible to detect unless you're looking for it specifically. A technological object doesn't have to look like a science fiction spaceship. It could look like a rock. It could be covered in dust and ice accumulated over millions of years of travel through interstellar space. It could make course corrections so subtle that we'd need incredibly precise measurements over long time periods to even notice. And that's exactly why the October 29th moment matters so much. It's not just that we can't observe Atlas during perihelion, it's that if something does happen, if there is a manoeuvre, we'll have lost our best chance to detect it in real time. We'll be left with before and after data, and a gap in the middle where the most important thing might have occurred. Loeb describes this as a hidden vantage point, and I think that phrase captures the problem perfectly. If you wanted privacy for a manoeuvre, you'd take it at the one moment when the most advanced observers can't see you. And Atlas arrives at that moment with timing precision that shouldn't exist for a random interstellar rock. So let's take stock of where we are with the trajectory analysis. Orbital inclination aligned with the ecliptic one in 500 odds. Close approaches to 3 planets with timing synchronization, 1 in 20,000 odds. Perihelion occurring during Earth's solar conjunction, additional improbability, depending on how you calculate arrival time variance. Stack those probabilities, multiply them together, and you get numbers that make statisticians uncomfortable. Not impossible numbers, just really unlikely numbers for something that's supposed to be random. And here's the thing that keeps me up at night about this we're not done yet. The trajectory is just one piece of evidence. We haven't talked about the chemistry, the visual observations, the things Hubble and Webb saw that don't quite fit the comet model. Each additional anomaly makes the coincidence explanation a little harder to swallow. But for now, for the trajectory alone. Loeb's argument is this: Atlas is either phenomenally lucky, or it's following a plan. And on October 29th, we might start to find out which one it is. 26 days. That's how long we have before Atlas reaches perihelion and vanishes behind the sun. 26 days to observe, to measure, to figure out what we're actually looking at before the most critical moment happens in complete darkness. Let me walk you through what October 29th actually means, because this isn't just about a date on a calendar. This is about orbital mechanics, gravitational physics, and a window of opportunity that, if Atlas is anything other than a random rock, represents the single most important decision point in this entire encounter. First, let's talk about what perihelion is and why it matters. When an object orbits the Sun, its path is an ellipse, or in Atlas's case, a hyperbola, since it's moving faster than escape velocity. Perihelion is the point of closest approach, the moment when the object is nearest to the Sun and therefore moving at its maximum velocity. For Atlas, perihelion occurs at about 1.4 astronomical units from the Sun. That's just inside Mars's orbit, well into the inner solar system where solar radiation is intense and gravitational forces are strongest. At that distance, Atlas will be travelling at roughly 50 kilometers per second relative to the Sun. That's 180,000 kilometers per hour, fast enough to cross the distance from Earth to the Moon in about 2 hours. And here's why that speed matters: the Oerth effect, named after German physicist Hermann Oberth. This principle is fundamental to spaceflight. It states that if you want to change your velocity, speed up or slow down, the most efficient time to do it is when you're already moving fast near a massive object. The math is counterintuitive at first, but it works like this: kinetic energy increases with the square of velocity. So if you're moving at 50 kilometers per s and you add just 1 kilometer per s of thrust, You gain way more energy than if you were moving at 10 kilometers per s and added the same 1 kilometer per s. It's like the difference between accelerating a car that's already doing 100 miles per hour versus one that's sitting still. The faster you're going, the more impact each additional unit of speed has on your total energy. Every spacecraft we've sent to the outer solar system uses this effect. Voyager 1 and 2 use Jupiter's gravity to slingshot towards Saturn and beyond, firing their engines at closest approach to maximize the velocity gain. New Horizons did the same thing. It's not a trick, it's just physics exploited efficiently. Now flip it around. The oerth effect works in reverse too. If you want to slow down, to bleed off velocity and let gravity capture you into a bound orbit, the most efficient place to do it is at perihelion when you are moving fastest. You fire engines or use whatever propulsion system you have to reduce your velocity by just a few kilometers per second. And the sun's gravity does the rest. Instead of escaping back into interstellar space, you get trapped in an elliptical orbit around the sun. It's called orbital capture, and it's exactly what you'd do if you wanted to transition from passing through a star system to staying in it permanently. For Atlas, the math is straightforward. Right now, it's on a hyperbolic trajectory with an excess velocity, the speed beyond escape velocity of about 3 to 4 kilometers per second. If Atlas were to slow down by roughly that amount at perihelion, it would drop below escape velocity. The sun's gravity would capture it, and instead of leaving the solar system in a few months, it would stay, looping back around in an elliptical orbit that could last thousands or millions of years. 3 to 4 kilometers per second, that's all it takes. For context, that's less than the delta V budget of a SpaceX Starship. Chemical rockets can do that easily. Ion drives can do it more efficiently with less fuel. Any advanced propulsion system would handle it trivially, so the capability required for orbital capture is well within known physics. The question isn't whether it's possible. The question is whether Atlas has the ability to do it and whether it will... And that brings us to the timing problem. October 29th isn't just when Atlas reaches perihelion. It's when Earth is positioned on the exact opposite side of the Sun, solar conjunction, maximum separation. The Sun directly between us and the object we're trying to observe. From Earth's perspective, Atlas will be about 2 astronomical units away, twice the Earth-Sun distance, but geometrically positioned such that any line of sight to it passes through the Sun's corona. Ground-based telescopes will see nothing. The sun's glare drowns out everything within several degrees of its visual position. You can't point a telescope at the sun and expect to see a faint comet behind it. You'll just burn out your sensors. Space-based telescopes fare slightly better, but not much. Hubble can't observe anything within about 50 degrees of the sun without risking damage to its instruments. Webb has similar restrictions. Even SOHO and the Solar Dynamics Observatory, which are designed to look at the sun, can't resolve a small object embedded in the corona's scattered light. We will be blind for approximately 10 to 14 days around perihelion. Atlas will be completely unobservable from Earth. It enters the conjunction zone in late October, passes through perihelion on the 29th, and doesn't re-emerge into observable space until mid-November. 2 weeks of darkness at the single most critical moment in the entire flyby. Lobe looks at that timing and asks a question that makes a lot of scientists deeply uncomfortable. How likely is this to happen by chance? If you take Atlas's trajectory and randomly vary its speed slightly, shift its arrival time at perihelion by a few weeks earlier or later, what are the odds that it would arrive precisely when Earth is on the opposite side of the Sun? The calculation depends on how much variance you allow, but it's somewhere in the range of 1 in 20 to 1 in 50. Not astronomically unlikely, but definitely notable. Definitely something that raises an eyebrow when you add it to all the other improbabilities we've been stacking. And here's where Loeb's tactical analysis gets really interesting. He points out that if you were designing an interstellar probe with instructions to survey a star system, you'd want to gather data without revealing your presence. You'd want to observe without being observed. And if you needed to make a major course correction, something as significant as transitioning from a flyby trajectory to a permanent orbit, you'd want to do it when the most technologically advanced planet in the system can't see you. October 29th gives you that. It's not just convenient, it's optimal from both a physics standpoint and an operational security standpoint. The oerth effect maximizes your propulsion efficiency. The solar conjunction maximizes your concealment. You get the best of both worlds, maximum capability at the exact moment of minimum observability. Loeb uses the phrase hidden vantage point to describe this, and I think it's perfect. Atlas isn't just passing behind the sun. It's positioned such that any maneuver it makes will be completely invisible to us. Now, let's be very precise about what we will and won't know after perihelion. When Atlas re-emerges in mid-November, astronomers will immediately begin tracking its position and calculating its new orbit. Within a few days, maybe a week, they'll have enough data to determine whether the trajectory changed. If Atlas is still on a hyperbolic escape path, same velocity, same direction, just continuing its exit from the solar system, then nothing happened. It's just a comet. Interesting one. Sure, but ultimately natural. But if the orbit has changed, if Atlas is now on an elliptical path that keeps it bound to the sun, we'll know a maneuver occurred. We just won't know the details. We won't know when exactly during the conjunction window the burn happened. We won't know what kind of propulsion was used. We won't see any exhaust plumes or heat signatures or direct evidence of artificial thrust. We'll only see the before and after, the trajectory going in and the trajectory coming out. And that gap, that missing data at the most important moment, is what makes Loeb nervous. Because here's the thing about science: we build models based on observations. We test hypotheses by predicting outcomes and measuring results. But when you can't observe the thing that matters most, when the critical event happens in darkness, you lose the ability to distinguish between different explanations. Did Atlas make a powered maneuver to capture itself into orbit, or did it encounter some unexpected gravitational perturbation, maybe a previously unknown asteroid or density fluctuation in the solar wind that changed its trajectory naturally, without observing the event? You can't say for certain. Loeb argues that this ambiguity is unacceptable given the stakes. If there's even a small chance Atlas is technological, if there's even a 1% probability that we're looking at an alien probe rather than a natural comet, then we need to be watching it during perihelion. Not watching from Earth, that's impossible, but watching from somewhere. And here's where things get interesting, because we do have assets positioned to potentially observe Atlas during the conjunction window, not perfectly, not with ideal geometry, but better than nothing. ESA's JUICE spacecraft is currently en route to Jupiter, but it's still relatively close to Earth's orbit. Its position in late October will give it a view of Atlas from a different angle than Earth. Not directly, not with perfect sightlines, but good enough to potentially catch something if Atlas makes an obvious maneuver. JUICE carries cameras, spectrometers, particle detectors. If Atlas produces any kind of exhaust or waste heat or electromagnetic signature during a burn, JUICE might detect it. The data won't arrive immediately. JUICE is far enough from Earth that its telemetry comes back slowly, but by early 2026, we should have whatever observations it managed to capture. NASA's Juno probe, currently orbiting Jupiter, will also have a distant view of Atlas in late October. Not as good as JUICE's geometry, but worth checking. Every data point matters. And then there are the Mars orbiters. Atlas passes closest to Mars on October 3rd, weeks before perihelion, but those spacecraft will continue tracking it as long as it's visible from Mars's position. Mars Reconnaissance Orbiter, Mars Express, the trace gas orbiter. All of them could potentially catch the tail end of Atlas's approach to perihelion before it enters solar conjunction from Mars's perspective too. Loeb's argument is that we should be coordinating all these assets. We should be pooling data from every spacecraft in the inner solar system to make sure we don't miss anything during the October 29th window, because if Atlas does make a maneuver, if it does capture itself into orbit, the implications are staggering. It would mean we have a visitor that's not just passing through. Something that chose to stay. Something that made a deliberate decision to set up shop in our solar system. And the question that follows immediately is why? What would be the purpose of staying? What does Atlas or whatever intelligence might have built it want with our neighbourhood? Loeb suggests several possibilities, and none of them are comforting. Best case, it's a scientific probe. An automated explorer sent by some long-dead civilization to study star systems and gather data. It arrives, captures into orbit, spends years or decades observing Earth and the other planets, then transmits its findings back to wherever it came from. We might never even know it's doing this. We might never detect any active sensors or communications. It could just be watching quietly, learning about us the way we send probes to study Mars or Jupiter. Middle case, it's a resource scout. An advanced civilization sends probes to catalogue star systems, identify useful materials, water, ice, metals, organic compounds, and mark them for future exploitation. Atlas stays in orbit, maps the asteroid belt, surveys the moons of Jupiter, and eventually sends coordinates back home. We'd be on someone's list, a target for mining or colonization or whatever resource extraction looks like at interstellar scales. Worst case, it's defensive. The dark forest hypothesis that Loeb occasionally references suggests that revealing your existence to other civilizations is dangerous because you can't know their intentions. The safest strategy might be preemptive elimination, destroy any emerging intelligence before it becomes a threat. In that scenario, Atlas staying in orbit isn't scientific curiosity, it's reconnaissance before an attack. Loeb is careful to frame all of this as speculation. He's not predicting doom. He's not claiming Atlas is definitely a weapon. But he is saying we can't rule it out based on the data we have, and that uncertainty should drive us to gather better data as quickly as possible. Because here's the asymmetry he keeps highlighting: the cost of investigating thoroughly and finding out Atlas is natural is minimal. We spend some telescope time, some research funding, and we learn interesting things about interstellar comets. But the cost of assuming it's natural and being wrong of missing a genuine technological visitor because we dismissed it too quickly as catastrophic. We'd lose the opportunity to establish contact with an alien intelligence. We'd miss warning signs if the visitor turned out to be hostile. We'd fail at the one moment in human history when the universe handed us something extraordinary and asked if we were paying attention. October 29th is that moment. 26 days from now, Atlas disappears behind the sun, and when it re-emerges in mid-November, we'll start getting answers. Either the trajectory is unchanged and it's just a comet, or the trajectory has shifted and we're living in a different universe than we thought, one where we're not alone, where interstellar travel is real, and where something out there decided our solar system was worth a closer look. Let's talk about what 33 billion tons actually means, because this number isn't just big, it's diagnostic. It tells us something fundamental about what Atlas is made of, how it's structured, and whether the natural comet explanation still holds up under scrutiny. Start with the basic physics. When gas jets off a comet's surface, when ice sublimates and throws material into space, it creates thrust. Newton's third law, action and reaction. The gas goes one way, the comet gets pushed the other way. This is measurable. It's called non-gravitational acceleration, and every active comet we've ever studied shows it. You track the comet's position over time, compare it to where pure gravity says it should be. And the difference tells you how much the outgassing is pushing it around. For small comets, this effect is huge. 67P/Churyumov-Gerasimenko, the comet that Rosetta visited, weighs about 10 billion tons and shows non-gravitational acceleration that's easily measurable, several meters per day squared. For Atlas, with 150 kilograms per second of gas streaming off its surface, you'd expect similar acceleration. Maybe not as dramatic as Churyumov-Gerasimenko because Atlas is bigger, but definitely detectable. But the observations show almost nothing, less than 15 meters per day squared. That's the upper limit. The actual acceleration could be even smaller, possibly zero within measurement error. So you've got this equation: thrust from outgassing equals mass times acceleration. We know the thrust 150 kilograms per s of gas moving at typical sublimation velocities gives you a force you can calculate. We know the acceleration basically zero. That leaves mass as the only variable that can make the equation balance. And the mass has to be enormous. Loeb's team worked through this calculation using observations from 227 observatories worldwide. Over 4,000 data points spanning months of tracking. The precision on Atlas's position is absurdly good down to fractions of an arcsecond on the sky. And the number that falls out of the math is 33 billion tons minimum. That's not the most likely mass. That's the absolute floor. Atlas can't weigh less than that, or we'd see it getting pushed around by its own gas jets. It could weigh more, possibly significantly more, but 33 billion tons is the lower bound. Now, here's where it gets interesting. If you assume Atlas is made of typical comet material, water ice, carbon dioxide ice, dust, rocky silicates, you can estimate its density. Most comets we've studied in detail have densities between 400 and 600 kilograms per cubic meter. That's about half the density of water. Lighter than you'd think, right? But it makes sense because comets are porous. They're not solid chunks of ice. They're more like cosmic snowballs, loosely packed, full of voids and gaps, held together by weak gravity and frozen volatiles. Take 33 billion tons, that's 3.3 times 10 to the 13th kilograms, and assume a density of 500 kilograms per cubic meter. Work backward to get volume, then calculate the diameter of a sphere with that volume. You get about 5 to 6 kilometers. So even with the revised mass estimate, Atlas is still big. Not the initial 20-kilometer calculation, but definitely on the large end for interstellar visitors. And that brings us right back to the statistical distribution problem. Objects that size should be rare. We should be finding thousands of smaller ones first. But there's another possibility, one that Loeb hints at but doesn't fully commit to in his public statements. Though it's clear from his papers that he's thinking about it carefully. What if Atlas isn't porous like a normal comet? What if it's hollow? Think about the difference. A porous comet is like a sponge, lots of tiny voids throughout the structure, but still fundamentally solid material with gaps. A hollow object is different. It's a shell, a thin outer layer with a large empty space inside. The International Space Station is hollow. It's over 100 meters across, but it doesn't weigh much relative to its volume because most of that volume is empty space. The structure is just walls, equipment, and living areas. The bulk of it is vacuum. If you saw the ISS from a distance and assumed it was a solid chunk of metal, you'd overestimate its mass by orders of magnitude. Now scale that up. A spherical shell 10 kilometers in diameter, with walls maybe a few hundred meters thick, could easily weigh 33 billion tons depending on what it's made of. From the outside, it would look like a large solid object. It would reflect sunlight. It would accumulate dust and ice on its surface as it travelled through interstellar space. After millions of years of drifting through molecular clouds, It could be completely coated in frozen volatiles water ice. CO2 organic compounds frost on the windshield, and when it got close to a star and started heating up, that surface ice would sublimate, it would outgas. It would look exactly like a comet from the outside, but underneath, it could be something completely different. Loeb doesn't say Atlas is definitely a hollow artificial structure in any of his interviews, but he does say this. We shouldn't judge a book by its cover. The chemical composition we're detecting could just be material that collected on the exterior during its journey. That's a careful statement. It leaves room for the natural explanation maybe Atlas really is just an unusually dense comet with a composition we haven't seen before. But it also leaves room for the technological explanation. Maybe what we're looking at is a surface layer that doesn't represent the bulk composition at all. And here's where the density calculation becomes really important. If Atlas is a solid object made of ice and rock with a density around 500 kilograms per cubic meter, then 33 billion tons gives you that 5 to 6 kilometer diameter. The numbers work. It's unusual but not impossible. But what if the density is higher? What if Atlas is made of denser material? Rocky asteroids have densities around 2000 to 3000 kg per cubic meter. Metallic asteroids can be even denser, up to 7000 or 8000 kg per cubic meter for iron-nickel compositions. If Atlas were made of rock with a density of 500 kilograms per cubic meter, that 33 billion ton mass gives you a diameter of only about 3 kilometers. Much smaller. If it were made of metal, you'd get even smaller, maybe 2 kilometers across. But we're seeing an object that appears much larger than that when we observe it. The coma, the cloud of gas and dust, extends for hundreds of thousands of kilometers. The brightness calculations initially suggested something 10 to 20 kilometers across. So either the object is genuinely large and low density like a normal comet, or it's smaller and higher density with a huge amount of surface outgassing, making it appear bigger than it really is. Or, and this is the third option that keeps nagging at the data, it's large in volume but low in mass because it's not solid. Here's why this matters. If Atlas is hollow, if it's a constructed shell rather than a natural accumulation of ice and rock, then the 33 billion ton mass isn't an anomaly. It's a design parameter. You build an interstellar probe. You want it to be as light as possible to minimize the energy needed for acceleration and deceleration. But you also need enough mass to resist perturbations, cosmic rays, impacts from interstellar dust, and yes, thrust from surface outgassing as you pass through a star system. 33 billion tons is heavy enough to be stable, but light enough to be practical for a structure tens of kilometers across. It's the kind of number that makes sense if you're engineering something. Now, before you accuse me of going full ancient aliens here, let me be clear about what the evidence actually shows. We don't have any direct proof that Atlas is hollow. We can't see inside it. We haven't done radar imaging or seismic analysis or any of the techniques we'd use to probe internal structure. All we have is the external measurements mass, brightness, outgassing rate, trajectory, and those measurements are consistent with a natural comet. Definitely. But they're also consistent with something else. And until we gather better data, until we get close enough to actually image the nucleus clearly, to measure its rotation rate, to analyze its shape and surface features, we can't rule out the technological hypothesis. Loeb's point is that we shouldn't rule it out prematurely. We shouldn't assume Atlas is natural just because natural explanations exist. We should investigate thoroughly and let the data tell us what we're looking at. And the HiRISE images from the Mars flyby on October 3rd might give us that data. HiRISE was designed to photograph the Martian surface at resolutions down to about 30 centimeters per pixel from orbit, pointed at Atlas from 29 million kilometers away. It obviously won't get that kind of resolution, we're talking more like 30 kilometers per pixel. But that's enough to separate the nucleus from the coma. Enough to see if the central object is spherical or elongated or irregular. Enough to measure its size directly instead of inferring it from brightness. If HIRISE shows a nucleus that's 5 or 6 kilometers across, consistent with the 33 billion ton mass and typical comet density, then the natural explanation looks stronger. But if the nucleus is larger, 10 or 15 kilometers, and still weighs only 33 billion tons, then the density drops below what we'd expect for a normal comet. And you start asking questions about internal structure. Or if the nucleus is smaller, just a few kilometers, and still producing the observed brightness and outgassing, then you're looking at something that's either incredibly active for its size or reflecting light in an unusual way. Any of those outcomes pushes Atlas further into anomaly territory. And here's the thing that keeps bothering me about this whole mass calculation. It's not just that 33 billion tons is heavy, it's that the measurement technique is so robust. Loeb's team didn't estimate the mass. They derived it from fundamental physics. If Atlas is outgassing at 150 kilograms per s, and we know it is because Webb measured it directly, and if it's not accelerating detectably, and we know it's not because 227 observatories tracked its position precisely, then the mass has to be at least 33 billion tons. There's no wiggle room there. The physics is airtight, so you can't argue that the mass estimate is wrong without arguing that either the outgassing measurement is wrong or the position measurements are wrong, and both of those have been verified independently by multiple instruments. The mass is real. The question is what kind of object has that mass? Loeb uses an analogy I think captures this perfectly. He says, if you see an object floating in water and it's not sinking, you know its density is less than water. You don't need to lift it out and weigh it. The buoyancy tells you everything you need to know about its mass relative to its volume. Atlas's lack of non-gravitational acceleration is like buoyancy. It's a physical constraint that tells us about the mass-to-thrust ratio, and that ratio is way higher than we'd expect for a normal comet. Something is off. Either the composition is unusual, much denser than typical comets, or the structure is unusual, hollow or layered in ways that natural formation wouldn't produce. And when you combine this mass anomaly with all the other anomalies we've already discussed, the brightness, the trajectory, the timing, the picture that emerges is an object that doesn't quite fit the mould. Not obviously artificial, not definitely technological, just strange enough to warrant closer examination, and we're running out of time for that examination. October 3rd is the Mars flyby. October 29th is perihelion and blackout. After that, Atlas will be receding, getting fainter, harder to observe. The window for good data is closing fast. August 6th, 2025. The James Webb Space Telescope turned its infrared spectrometers toward Atlas and took a molecular census of the gas streaming off its surface. What it found was wrong. Not wrong in the sense of measurement error. The data was clean, well calibrated, confirmed by multiple observation runs. Wrong in the sense that it doesn't match what comets are supposed to look like chemically. The ratio of carbon dioxide to water ice in the coma 8:1. For every molecule of water vapour, there are 8 molecules of CO2. Let me give you context for why that number is deeply strange. Water is everywhere in the universe. It's the most abundant molecule after molecular hydrogen. Every comet we've studied in our solar system, Halley, Hale-Bopp, 67P, dozens of others, is predominantly water ice with traces of other volatiles mixed in. Typical ratios may be 10 to 20% carbon dioxide relative to water. Some comets go as high as 30 or 40% if they formed in particularly cold regions of the solar nebula, but that's rare. 8:1 is the inverse. Atlas is 89% carbon dioxide by molecular count. With water as the minor component, that's not just unusual, it's almost unique. Only one other comet in the entire catalogue of observations has shown a CO2 to water ratio anywhere near this extreme. C2016R2 discovered in 2016, which had an even more extreme ratio but was much smaller and behaved very differently in other ways. So where does carbon dioxide-dominated ice come from? The standard explanation is formation environment. Water ice is stable across a wide range of temperatures and distances from a star. You can find it everywhere from the inner solar system to the Kuiper belt. But carbon dioxide ice is more temperature sensitive. Close to a star, CO2 sublimates, turns directly from solid to gas at relatively low temperatures. It doesn't stick around unless you're far out where it's cold enough. Really cold, beyond Neptune cold. The most CO2-rich objects we know in our solar system are the trans-Neptunian objects, and certain comets from the Oort cloud, the vast spherical shell of icy bodies that orbits the Sun at distances of tens of thousands of astronomical units. If Atlas has an 8:1 ratio, it suggests it formed in an extremely cold environment, farther from its parent star than anything we have in our solar system's inner regions. Loeb points to this as potential evidence of extreme age or exotic origin. He suggests Atlas could have formed when its home star system was younger and colder, or in the outer reaches of a system very different from ours, maybe orbiting a dim red dwarf where the habitable zone is so close to the star that anything planet-sized is scorched. And the only stable ice exists in the outer darkness. And this is where the chemistry starts supporting the technological hypothesis. The CO2 isn't original composition at all. It's accumulated frost. Think about an object travelling through interstellar space for millions of years. The space between stars isn't empty. It's filled with diffuse gas and dust, mostly hydrogen, but also carbon, oxygen, nitrogen, all the elements that make up molecules. In some regions, particularly in molecular clouds, you get concentrations of carbon dioxide. It's been detected spectroscopically in interstellar ice. If Atlas passed through one of these clouds during its journey, CO2 molecules could condense on its cold surface and freeze there, layer after layer, over millions of years. By the time it arrives at a new star system, the surface could be coated with carbon dioxide ice that has nothing to do with the object's original composition. It's a protective layer, insulation, frost on the windshield. And when Atlas gets close to the Sun and that frost starts sublimating, the outgassing is dominated by whatever accumulated on the outside, not by whatever the core is made of. This is the argument Loeb keeps making. Surface observations don't necessarily tell you about interior composition. A book's cover doesn't tell you what's written inside. But here's where the chemistry gets even more interesting and more contradictory. In early August, before Webb took its measurements, astronomers at Kitt Peak National Observatory in Arizona analysed Atlas using optical spectroscopy. They were looking for specific molecular signatures, carbon chains, cyanide compounds, the usual suspects you find in comet comas. And they found something unexpected. Atlas was among the most carbon chain depleted comets known. Extremely low levels of C2 and C3 molecules. The diatomic and triatomic carbon that normally produces the green glow we associate with comets. So in early August, the spectroscopy said very little carbon chemistry happening here. Then in early September, during a total lunar eclipse when the moon was darkened and sky conditions were exceptional, two astrophotographers in Namibia captured deep images of Atlas, and it was glowing vivid green. Not a subtle tint, unmistakable, saturated green, the kind of colour that comes from diatomic carbon fluorescing under ultraviolet radiation from the sun. But the spectroscopy a month earlier said there wasn't much diatomic carbon present. So where did the green come from? One explanation, the carbon was always there. just buried beneath the surface. As Atlas got closer to the Sun and heating intensified, deeper layers of ice melted away, exposing fresh material that contained more carbon compounds. The green glow represents interior ice that was previously locked away. That would make sense if Atlas has a layered structure, different compositions at different depths, like geological strata in a cliff face. Another explanation, proposed by Loeb in a blog post after the green images came out, the colour might not be from diatomic carbon at all. It might be from cyanide. The Very Large Telescope in Chile detected a steep rise in cyanide production from Atlas in late August. The CN emission line, the spectroscopic signature of cyanide radical, increased dramatically as the comet approached the Sun. Cyanide can produce a greenish colour under certain conditions. If the concentrations are high enough and the excitation from solar UV is intense enough, it might explain the vivid hue captured during the eclipse. But cyanide production increasing suddenly, that's also strange. Comets don't usually switch on cyanide emission like flipping a switch. It's a gradual process tied to temperature and solar flux. Unless, and this is where Loeb's speculation gets really provocative, the green glow represents some kind of activation. He doesn't quite say this directly in interviews, but the implication is there in his writings. What if Atlas crossed a temperature threshold that triggered a change in its behaviour? What if systems that were dormant during the cold transit through interstellar space powered on as surface temperatures rose? An automated probe in hibernation mode might wake up as it approaches a star. Temperature would be the obvious trigger. An activation might produce byproducts heat, light, chemical emissions that we'd interpret as natural outgassing but which actually represent something very different. Again, this is speculation. There's no direct evidence for it, but it fits the pattern of a surface appearance that mimics natural processes while potentially concealing something artificial underneath. And then there's the temporal aspect of the green glow. It appeared suddenly, not gradually, not as a slow colour shift as the comet got brighter. One observation period, no green. Next observation period, vivid green. That's a threshold effect, a phase transition, something that happens when a system crosses a critical value temperature, pressure, radiation intensity, and shifts from one state to another. Natural processes can produce threshold effects, ice melting as threshold. Sublimation ramping up at specific temperature points is a threshold, so the green glow appearing suddenly isn't proof of anything artificial. But combined with everything else, the mass, the trajectory, the timing, the chemical ratios that don't quite fit, it's another data point in a growing collection of things that are individually explainable but collectively strange. Let's take stock of the chemical picture so far. Webb measured an 8:1 CO 2-to-water ratio. That's extreme, but not impossible for a comet from a very cold formation environment or one that accumulated surface frost during interstellar travel. Kitt Peak found low carbon chain abundance in early August. That's consistent with a young comet or one made of pristine ice without much organic contamination. But then Atlas glowed green in September, suggesting diatomic carbon or cyanide became abundant suddenly. And the Very Large Telescope detected rising cyanide emission around the same time. You can explain all of these observations with natural processes, layered composition, temperature thresholds triggering sublimation of buried ice, solar UV exciting different molecules at different distances. But the timing is tight, the transitions are sharp, and the overall chemical profile doesn't match any single comet archetype we have in our catalogue. It's like Atlas is sampling from multiple categories, ultra-cold formation here, organic poor composition there, sudden activation somewhere else without fitting cleanly into any of them. Loeb's argument is that this mosaic of properties is either an incredible coincidence or a sign that we're not looking at a purely natural object. that the surface chemistry might be a collection of accumulated materials rather than a coherent original composition. And if that's true, if the CO2 frost and the sudden green glow and the cyanide spike are all surface phenomena masking something deeper, then spectroscopy alone won't tell us what Atlas really is. We'd need to see beneath the surface. We'd need to probe the interior somehow, radar, seismic analysis, close-range imaging that can resolve structural details. And we're not going to get that before October 29th. The Mars flyby on October 3rd will give us HIRISE images of the nucleus. But HIRISE is an optical camera. It sees reflected light. It can measure size and shape, maybe surface texture, but it can't see inside. The chemistry will remain ambiguous. The surface composition will remain a puzzle. And when Atlas disappears behind the sun on the 29th, we'll still be working with incomplete data, trying to decide if we're looking at the weirdest natural comet ever observed or the most carefully camouflaged artificial object. Lobe keeps emphasizing this uncertainty. He says the data we have doesn't prove Atlas is technological, but it also doesn't rule it out. And in the absence of definitive proof either way, we should be investigating thoroughly instead of assuming, because chemistry can lie, surface composition can mislead, and if there's one thing we've learned from studying planets and moons in our own solar system, it's that what you see on the outside doesn't always represent what's inside. Jupiter looks like a gas giant from orbit, cloudy, turbulent, mostly hydrogen and helium. But compress that hydrogen under enough pressure and it becomes metallic. The interior is nothing like the exterior. Saturn's moon, Enceladus, looks like a frozen snowball from a distance. But crack open the ice shell and you find a global ocean of liquid water beneath. Surface observations are a starting point, not a conclusion. And with Atlas, the surface chemistry is strange enough to make you wonder what's underneath that 8.1 CO2 frost. What's beneath the layer that suddenly started glowing green? What kind of object needs that much carbon dioxide ice as a coating? August 6th, 2025. The James Webb Space Telescope turned its infrared spectrometers toward Atlas and took a molecular census of the gas streaming off its surface. What it found was wrong. Not wrong in the sense of measurement error. The data was clean, well calibrated, confirmed by multiple observation runs. Wrong in the sense that it doesn't match what comets are supposed to look like chemically. The ratio of carbon dioxide to water ice in the coma 8:1. For every molecule of water vapour, there are 8 molecules of CO2. Let me give you context for why that number is deeply strange. Water is everywhere in the universe. It's the most abundant molecule after molecular hydrogen. Every comet we've studied in our solar system, Halley, Hale-Bopp, 67P, dozens of others, is predominantly water ice with traces of other volatiles mixed in. Typical ratios may be 10 to 20% carbon dioxide relative to water. Some comets go as high as 30 or 40% if they're formed in particularly cold regions of the solar nebula, but that's rare. 8:1 is the inverse. Atlas is 89% carbon dioxide by molecular count, with water as the minor component. That's not just unusual, it's almost unique. Only one other comet in the entire catalogue of observations has shown a CO2 to water ratio anywhere near this extreme C2016 R2 discovered in 2016, which had an even more extreme ratio but was much smaller and behaved very differently in other ways. So where does carbon dioxide dominated ice come from? The standard explanation is formation environment. Water ice is stable across a wide range of temperatures and distances from a star. You can find it everywhere from the inner solar system to the Kuiper belt, but carbon dioxide ice is more temperature sensitive. Close to a star, CO2 sublimates turns directly from solid to gas at relatively low temperatures. It doesn't stick around unless you're far out where it's cold enough. Really cold, beyond Neptune cold. The most CO2-rich objects we know in our solar system are the trans-Neptunian objects, and certain comets from the Oort cloud, the vast spherical shell of icy bodies that orbits the Sun at distances of tens of thousands of astronomical units. If Atlas has an 8:1 ratio, it suggests it formed in an extremely cold environment, farther from its parent star than anything we have in our solar system's inner regions. Loeb points to this as potential evidence of extreme age or exotic origin. He suggests Atlas could have formed when its home star system was younger and colder, or in the outer reaches of a system very different from ours, maybe orbiting a dim red dwarf where the habitable zone is so close to the star that anything planet-sized is scorched, and the only stable ice exists in the outer darkness. And this is where the chemistry starts supporting the technological hypothesis. The CO2 isn't original composition at all. It's accumulated frost. Think about an object travelling through interstellar space for millions of years. The space between stars isn't empty. It's filled with diffuse gas and dust, mostly hydrogen, but also carbon, oxygen, nitrogen, all the elements that make up molecules. In some regions, particularly in molecular clouds, you get concentrations of carbon dioxide. It's been detected spectroscopically in interstellar ice. If Atlas passed through one of these clouds during its journey, CO2 molecules could condense on its cold surface and freeze there, layer after layer, over millions of years. By the time it arrives at a new star system, the surface could be coated with carbon dioxide ice that has nothing to do with the object's original composition. It's a protective layer, insulation, frost on the windshield. And when Atlas gets close to the Sun and that frost starts sublimating, the outgassing is dominated by whatever accumulated on the outside, not by whatever the core is made of. This is the argument Loeb keeps making. Surface observations don't necessarily tell you about interior composition. A book's cover doesn't tell you what's written inside. But here's where the chemistry gets even more interesting and more contradictory. In early August, before Webb took its measurements, astronomers at Kitt Peak National Observatory in Arizona analysed Atlas using optical spectroscopy. They were looking for specific molecular signatures, carbon chains, cyanide compounds, the usual suspects you find in comet comas. And they found something unexpected. Atlas was among the most carbon chain depleted comets known. Extremely low levels of C2 and C3 molecules. The diatomic and triatomic carbon that normally produces the green glow we associate with comets. So in early August, the spectroscopy said very little carbon chemistry happening here. Then in early September, during a total lunar eclipse when the moon was darkened and sky conditions were exceptional, 2 astrophotographers in Namibia captured deep images of Atlas, and it was glowing vivid green. Not a subtle tint, unmistakable, saturated green, the kind of colour that comes from diatomic carbon fluorescing under ultraviolet radiation from the sun. But the spectroscopy a month earlier said there wasn't much diatomic carbon present, so where did the green come from? One explanation: the carbon was always there, just buried beneath the surface. As Atlas got closer to the sun and heating intensified, deeper layers of ice melted away, exposing fresh material that contained more carbon compounds. The green glow represents interior ice that was previously locked away. That would make sense if Atlas has a layered structure, different compositions at different depths, like geological strata in a cliff face. Another explanation, proposed by Loeb in a blog post after the green images came out, the colour might not be from diatomic carbon at all. It might be from cyanide. The Very Large Telescope in Chile detected a steep rise in cyanide production from Atlas in late August. The CN emission line, the spectroscopic signature of cyanide radical, increased dramatically as the comet approached the Sun. Cyanide can produce a greenish colour under certain conditions. If the concentrations are high enough and the excitation from solar UV is intense enough, it might explain the vivid hue captured during the eclipse. But cyanide production increasing suddenly. That's also strange. Comets don't usually switch on cyanide emission like flipping a switch. It's a gradual process tied to temperature and solar flux. Unless, and this is where Loeb's speculation gets really provocative, the green glow represents some kind of activation. He doesn't quite say this directly in interviews, but the implication is there in his writings. What if Atlas crossed a temperature threshold that triggered a change in its behaviour? What if systems that were dormant during the cold transit through interstellar space powered on? As surface temperatures rose, an automated probe in hibernation mode might wake up as it approaches a star. Temperature would be the obvious trigger, and activation might produce byproducts: heat, light, chemical emissions that we'd interpret as natural outgassing but which actually represent something very different. Again, this is speculation. There's no direct evidence for it, but it fits the pattern of a surface appearance that mimics natural processes while potentially concealing something artificial underneath. And then there's the temporal aspect of the green glow. It appeared suddenly, not gradually, not as a slow colour shift as the comet got brighter. One observation period, no green. Next observation period, vivid green. That's a threshold effect, a phase transition, something that happens when a system crosses a critical value temperature. Pressure, radiation intensity, and shifts from one state to another. Natural processes can produce threshold effects. Ice melting is a threshold. Sublimation ramping up at specific temperature points is a threshold, so the green glow appearing suddenly isn't proof of anything artificial. But combined with everything else, the mass, the trajectory, the timing, the chemical ratios that don't quite fit, it's another data point in a growing collection of things that are individually explainable but collectively strange. Let's take stock of the chemical picture so far. Webb measured an 8:1 CO 2-to-water ratio. That's extreme, but not impossible for a comet from a very cold formation environment or one that accumulated surface frost during interstellar travel. Kit Peak found low carbon chain abundance in early August. That's consistent with a young comet or one made of pristine ice without much organic contamination. But then Atlas glowed green in September, suggesting diatomic carbon or cyanide became abundant suddenly, and the Very Large Telescope detected rising cyanide emission around the same time. You can explain all of these observations with natural processes, layered composition, temperature thresholds triggering sublimation of buried ice, solar UV exciting different molecules at different distances. But the timing is tight, the transitions are sharp, and the overall chemical profile doesn't match any single comet archetype we have in our catalogue. It's like Atlas is sampling from a multiple categories ultra-cold formation here, organic poor composition there, sudden activation somewhere else without fitting cleanly into any of them. Loeb's argument is that this mosaic of properties is either an incredible coincidence or a sign that we're not looking at a purely natural object, that the surface chemistry might be a collection of accumulated materials rather than a coherent original composition. And if that's true, if the CO2 frost and the sudden green glow and the cyanide spike are all surface phenomena masking something deeper, then spectroscopy alone won't tell us what Atlas really is. We'd need to see beneath the surface. We'd need to probe the interior somehow: radar, seismic analysis, close-range imaging that can resolve structural details. And we're not going to get that before October 29th. The Mars flyby on October 3rd will give us high-rise images of the nucleus. But HiRISE is an optical camera. It sees reflected light. It can measure size and shape, maybe surface texture, but it can't July 21st, 2025. The Hubble Space Telescope captures its first detailed image of Atlas. Astronomers were expecting to see the classic comet structure. A bright nucleus, the solid core surrounded by a diffuse coma of gas and dust. And maybe the beginnings of a tail streaming away from the sun. What they got was confusing. There was a teardrop-shaped cocoon of dust coming off the nucleus. There was a hint of a tail, faint and barely visible. But the orientation looked wrong. Instead of a clear tail streaming away from the sun, which is what every comet tail in history has done, there was an extension of scattered light pointing toward the sun, forward-facing, like the comet had headlights. Loeb picked up on this immediately. He co-authored a paper titled "Could Atlas Be Alien Technology?" and one of the pieces of evidence cited was this unusual forward glow. He said, and I'm paraphrasing from his public statements, "Comets are identified by their tails, just like zebras are identified by their stripes. The tail always points away from the sun. Always. It's determined by solar wind and radiation pressure, not by the direction the comet is travelling. So when you see something pointing toward the sun, that's not normal comet behaviour." NASA scientists pushed back hard on this. They said the apparent forward extension was an imaging artifact, not a real physical feature. Here's what happens when you photograph a fast-moving object with long exposure times. The object moves during the exposure. You get motion blur. The light trails in the direction of motion, and if that direction happens to be toward the sun, if the comet is falling inward during the observation, the blur creates a streak that looks like forward-pointing emission, even though it's really just smeared background stars and scattered light from the object itself. Hubble tracked Atlas during the exposure to keep the comet centered in the frame. That tracking causes background stars to streak in the opposite direction. The combination can create false features that look structural, but are actually just artifacts of the imaging process. NASA's Tom Statler, program scientist for small bodies, was blunt about this. He said the forward glow was almost certainly motion blur, and that interpreting it as anything else was bad astronomy. And to be fair to NASA, they have a point. Astrophotography is tricky. Separating real features from instrumental artifacts requires careful analysis. You can't just look at an image and assume everything you see is physically real. But Loeb wasn't entirely convinced. He argued that while motion blur could explain part of what Hubble saw, the brightness and structure of the extension didn't quite match what you'd expect from pure smearing. He suggested that maybe there was something there. Some kind of forward emission that didn't fit the standard comet model. And then, late August happened. The Gemini South Telescope in Chile captured new images of Atlas. High resolution, good seeing conditions, long integration times with the proper tracking, and this time there was a clear tail, faint but unmistakable, streaming away from the sun exactly where you'd expect it. By late August, Atlas looked like a normal comet. Case closed, right, not quite. Because the timing bothers me, and it bothers Loeb too, though he's careful not to overstate the significance. For the first month and a half after discovery from early July through mid-August, Atlas showed ambiguous visual features. The forward glow in the Hubble images, the lack of a clear tail, the unusual brightness for an object that far from the sun, and then, right around the time it crossed inside Mars's orbit, right when solar heating really ramped up and surface temperatures crossed the threshold for intense water ice sublimation, it started to look more like a normal comet. Loeb uses that book analogy again. We shouldn't judge a book by its cover. The fact that Atlas now has a comet-like tail doesn't necessarily tell us what's underneath. Think about what happens to an object travelling through interstellar space for millions of years. It's cold, approaching absolute zero in the depths between stars. Any water vapour, any carbon dioxide, any volatile compounds it encounters, even in the ultra-low density of interstellar gas, will condense on its surface and freeze, layer after layer, molecule by molecule. Over millions of years, You build up a coating, frost on the windshield. And when that object finally enters a new star system and gets close enough to a star for solar radiation to heat the surface, that frost sublimates. The ice turns to gas. You get outgassing. You get a coma. You get a tail. You get all the visual signatures of a comet, even if the object underneath isn't a comet at all. This is the argument Loeb keeps making, and it's not scientifically unreasonable. An artificial object, a spacecraft, a probe, whatever you want to call it, wouldn't look pristine and metallic after millions of years in space. It would be covered in accumulated ice and dust. It would look dirty, organic, natural. And when it entered a star system and that coating started sublimating, it would produce exactly the kind of tail we're now seeing on Atlas. So the appearance of normal comet behaviour in late August doesn't rule out the technological hypothesis. It's consistent with it, if you assume there's something underneath the surface layer. But here's the flip side of that argument if you can explain any observation tail or no tail, forward glow or normal glow with the same hypothesis, then the hypothesis becomes unfalsifiable. It predicts everything and therefore predicts nothing. That's the criticism Loeb's colleagues keep throwing at him. They say his alien probe theory is too flexible, too accommodating of contradictory data. If Atlas behaves like a comet, he says the surface is disguised in something artificial. If it doesn't behave like a comet, he says that's evidence it's artificial. Either way, he arrives at the same conclusion. Loeb's response is that he's not trying to prove Atlas is technological. He's trying to show that the technological explanation remains viable given the data we have. And the burden of proof should go both ways. If you want to conclusively say Atlas is natural, you need to explain all the anomalies with natural processes. The mass, the trajectory, the timing, the chemistry, the visual evolution. And so far, no one's done that to his satisfaction. Every explanation requires stacking multiple low-probability events, multiple coincidences, well, it could happen if scenarios, at some point, Loeb argues, the collection of coincidences becomes less likely than the alternative explanation. But let's dig deeper into this visual evolution, because there's more going on than just the appearance of a tail. The green glow I mentioned earlier, the one that showed up during the September lunar eclipse, wasn't gradual. It was sudden. Astrophotographers had been imaging Atlas for weeks before the eclipse. None of those images showed significant green colour. The comet was bright. Yes, it had a developing coma. But the colour was mostly white or pale yellow, typical of dust scattering sunlight. Then the eclipse happened. The moon darkened completely. Sky conditions were exceptional, no lunar glare, no light pollution from the moon's reflection. Deep exposures became possible, and Atlas was vivid green, not subtle, not if you enhance the colour channels you can see a slight tint. Vivid, saturated, unmistakable. That suggests something changed. Either the chemistry of the coma shifted rapidly, different molecules being released as deeper ice layers sublimated, or our previous observations had missed the green component because of poor imaging conditions. But here's what makes it interesting. The timing coincides with the cyanide spike detected by the Very Large Telescope. Both the green colour and the CN emission line intensity ramped up in the same narrow time window. That's a correlation. Not proof of causation, but suggestive. If you're looking for natural explanations, you'd say Atlas crossed a temperature threshold where cyanide-bearing ice became volatile enough to sublimate efficiently. Solar UV hit those CN molecules, excited them, and they fluoresced green. Threshold effects happen in nature. Ice doesn't gradually melt, it stays solid until you hit the melting point. Then it transitions. Sublimation works the same way. You can have an object that's barely outgassing, and then it crosses a temperature boundary and suddenly starts gushing gas. so the sudden green glow could be natural. But if you're entertaining the technological hypothesis, you'd note that activation sequences also produce threshold effects. Systems in standby mode draw minimal power, produce minimal emissions, then they power up, and you get a spike in activity, heat signatures, chemical byproducts, light emission from instruments turning on. An automated probe entering a star system might stay dormant until surface temperatures indicated it was close enough to the star for observation and maneuvering to be worthwhile. Temperature could be the trigger, and activation might produce exactly the kind of sudden chemical signature we're seeing. Again, this is speculation layered on speculation. I'm not claiming this is what's happening. I'm walking through the logic Loeb is using to keep the technological option on the table. The point he keeps making is this: if you're not looking for artificial signatures, you won't find them. If you assume everything is natural, you'll interpret every observation through that lens. But if you're open to the possibility, if you allow for the hypothesis that some interstellar objects might be technological, then certain patterns start to look different. A forward glow that disappears when normal tail development begins could be instrument bloom from an active sensor suite that powered down when no longer needed. A sudden colour change could be outgassing from a propulsion system test, or temperature regulation vents opening. Surface composition dominated by CO2 frost could be deliberate thermal management insulation designed to protect interior systems from temperature extremes. None of these interpretations are necessary. All of the observations can be explained naturally, but they can also be explained artificially, and until we have definitive data ruling one out, both remain possibilities. The HiRISE images from October 3rd might help. If the nucleus has an irregular, potato-like shape typical of small comets and asteroids that supports natural formation, gravity alone doesn't make small objects spherical. You need enough mass for self-gravity to overcome structural strength, and that doesn't happen until you're a few hundred kilometers across. But if the nucleus is unusually smooth, or too spherical for its size, or shows geometric features, straight edges, regular patterns that would be harder to explain naturally, and if HiRISE catches any surface details, vents, cracks, colour variations, those could tell us about composition and structure in ways spectroscopy alone can't. We're days away from that data. October 3rd is almost here. And then 3.5 weeks later, Atlas vanishes behind the sun, and the entire visual record goes dark for 2 weeks. When it re-emerges in mid-November, we'll be looking for changes. Did the tail structure shift? Did the colour change? Is the outgassing rate different? Any variation between the pre-perihelion appearance and the post-perihelion appearance could indicate something happened during the blackout window. Or it could just be natural evolution as the comet continues heating up and different ice layers become exposed. This is the interpretive nightmare Loeb is navigating. Every observation is ambiguous. Every data point supports multiple explanations, and the critical moments, Mars flyby, perihelion, post-conjunction emergence, are spread across months, making it hard to see the full pattern until it's already happened. See inside. The chemistry will remain ambiguous, the surface composition will remain a puzzle, and when Atlas disappears behind the sun on the 29th, we'll still be working with incomplete data, trying to decide if we're looking at the weirdest natural comet ever observed or the most carefully camouflaged artificial object. Loeb keeps emphasizing this uncertainty. He says the data we have doesn't prove Atlas is technological, but it also doesn't rule it out. And in the absence of definitive proof either way, we should be investigating thoroughly instead of assuming, because chemistry can lie, surface composition can mislead, and if there's one thing we've learned from studying planets and moons in our own solar system, it's that what you see on the outside doesn't always represent what's inside. Jupiter looks like a gas giant from orbit, cloudy, turbulent, mostly hydrogen and helium. but compress that hydrogen under enough pressure and it becomes metallic. The interior is nothing like the exterior. Saturn's moon, Enceladus, looks like a frozen snowball from a distance. But crack open the ice shell and you find a global ocean of liquid water beneath. Surface observations are a starting point, not a conclusion. And with Atlas, the surface chemistry is strange enough to make you wonder what's underneath that 81CO2 frost. What's beneath the layer that suddenly started glowing green? What kind of object needs that much carbon dioxide ice as a coating? October 3rd, 3 days from now as I'm writing this. Mark it on your calendar, because it's the first moment of truth. Atlas will pass within 29 million kilometres of Mars. And if Loeb's calculations are correct, that's not just a close approach, it's a reconnaissance window. Let me walk you through the geometry, because this is where orbital mechanics becomes, let's call it suggestive. When Atlas reaches its closest approach to Mars, it won't just be near the planet in space. It'll be approaching from a specific angle, at a specific velocity, with a trajectory that would make it absurdly easy to deploy something toward Mars if you wanted to. Loeb ran the numbers. He calculated what would happen if Atlas released a smaller object, call it a secondary probe that travelled ahead of the main body and sideways by about 30 million kilometres. That probe, with an ejection velocity of just a few kilometres per second, could reach Mars right around October 3rd. Right when Atlas makes its closest approach, a few kilometres per second. That's nothing in space propulsion terms. That's a gentle push, not a violent ejection. Chemical thrusters could do it. Compressed gas could do it. A spring-loaded release mechanism could do it. And from Earth, we wouldn't see it. We can resolve objects down to maybe 10 or 20 metres at Jupiter's distance under ideal conditions. Smaller than that, they disappear into the noise. A probe the size of a car or small room, say 5 metres across, wouldn't show up in any telescope images we have of Atlas. It could separate from the main body weeks ago, make a slow course correction toward Mars, and we'd never know until it arrived. Now, is there any evidence that Atlas has deployed anything? No. None. Zero. This is pure speculation based on what would be possible given the trajectory and timing. But Loeb's point is that we should be watching. We should be looking specifically for anomalies during and after the October 3rd encounter. Because if something was going to happen, if Atlas is technological and has any interest in Mars, this would be the moment. And here's what makes this particularly nerve-wracking. Mars is surrounded by spacecraft. Ours, NASA, has multiple assets in orbit. Mars Reconnaissance Orbiter, MAVEN, Mars Odyssey, ESA has Mars Express and the Trace Gas Orbiter. All of them are active. All of them are monitoring the Martian environment. And all of them will be in position to detect anything unusual during the Atlas flyby. If a secondary object enters Martian orbit, if something approaches the planet and makes a capture burn or deploys additional hardware, those spacecraft should see it. But here's the problem, they're not specifically tasked with watching for this. They're not in a coordinated observing campaign looking for artificial objects entering Mars's sphere of influence. They're doing their regular science operations, monitoring the atmosphere, mapping the surface, tracking dust storms. An anomalous radar return or an unexpected visual sighting might get flagged in the data weeks or months later, but it wouldn't trigger an immediate alert unless someone was looking for it specifically. Loeb has been advocating for exactly that kind of coordinated watch. He wants NASA and ESA to task their Mars assets with monitoring for any unidentified objects during the October 3rd window. Watch the approach corridor. Watch for trajectory changes in Atlas itself. Watch for any secondary objects that separate and maneuver independently. As far as I can tell from public statements, there's no indication that's happening in an organised way. Individual teams might be interested. Individual scientists might keep an eye out, but there's no official protocol for watch for alien probes deploying secondary craft at Mars. Which means if something does happen, we might not notice it until someone reviews the data later and says, "Hey, what's that thing in the background of this image?" And by then, it would be too late to respond in real time. Now let's talk about why Mars specifically matters here. Because it's not just about proximity. Mars is interesting. It's the most Earth-like planet in the solar system. It had liquid water on its surface billions of years ago. It had a thicker atmosphere. It might have had life. We're still looking for evidence of that. If you're an interstellar probe designed to survey star systems and assess potential habitability, Mars would be on your list. Not as interesting as Earth, obviously, but interesting enough to warrant a closer look. And here's the thing, Mars is way easier to approach than Earth. Earth has a thick atmosphere that would burn up anything entering too fast without proper heat shielding. Earth has active space monitoring. We'd probably detect an incoming object. At least in the final approach phase, Earth is... well, Earth. It's crowded. It's watched. It's defended. As much as we can defend anything, Mars is quieter. Mars's atmosphere is thin, 1% of Earth pressure at the surface. You can land there with simple propulsion and parachutes. You can orbit there without much risk of detection if you're small and not broadcasting. If you wanted to deploy a surface probe somewhere in the inner solar system without immediately revealing your presence to the most technologically advanced planet, Mars would be the smart choice. You could land a probe on Mars, have it study the geology and look for biosignatures, and even if it operated for years, we might never find it. Mars is big. Our surface coverage with rovers and landers is minimal. There are vast regions we've never imaged at high resolution. A lander the size of a car could sit in Valles Marineris or the northern plains, and we wouldn't see it unless we happened to point a camera at exactly the right spot. So from a strategic standpoint, Mars during the October 3rd encounter is an opportunity. If Atlas has any capability to deploy secondary assets, this is when you do it. But let's step back and ask the more fundamental question, why would an interstellar probe deploy anything at all? What's the logic? If you're a civilization capable of sending probes across light years of space, you're probably not doing it casually. Interstellar travel is expensive energetically, temporally, resource-wise. You don't send something to another star system without a purpose. Scientific exploration is the obvious answer. You want to study other solar systems, catalogue planets, look for life or interesting chemistry. A primary vessel on a fast flyby trajectory can gather data, but it's limited. You're moving at high speed, observations are brief, resolution is constrained, deploying smaller probes that can stay behind, orbit planets, maybe even land and do long-term studies that multiplies your science return enormously. We do this with our own missions. Cassini orbited Saturn for over a decade and deployed the Huygens lander to Titan's surface. We didn't just fly past, we stuck around. We studied the system in depth. If Atlas is a scientific mission, deploying a Mars probe makes perfect sense. But there are darker possibilities. Resource assessment. If you're scouting star systems for future exploitation mining, colonization, whatever advanced civilizations do with raw materials, you'd want detailed surveys of rocky planets and moons. Mars has water ice. It has minerals. It has potential as a way station or resource depot. A deployed probe could map resources, identify deposits, catalogue what's available for extraction, or reconnaissance before contact. If you're planning to approach Earth but you want to gather intelligence first, understand technological capabilities, assess threat levels, figure out communication strategies. You might start with Mars, deploy a probe there, watch Earth from a distance, monitor radio transmissions, observe space activity. build a profile of the civilization before making direct contact, or defensive preemption, the dark forest hypothesis. Loeb occasionally references suggest that revealing your existence to other civilizations is dangerous because you can't predict their intentions. The safest strategy might be to eliminate potential threats before they mature. A probe at Mars could be the first stage of that. Establish a forward operating position, monitor the target, wait for instructions or triggering conditions. I'm not saying this is what's happening. I'm walking through the logical possibilities if we take the technological hypothesis seriously. And Loeb's argument is that we should take it seriously enough to at least watch carefully during the October 3rd window. Because if something does deploy and we miss it, if there's a secondary object that enters Martian orbit or lands on the surface and we don't notice until months later, that's a failure of preparedness. We had warning, we had time, we had assets in position, and we didn't watch closely enough because we assumed nothing would happen. Now, let's talk about what actually happens on October 3rd from an observational standpoint. Mars Reconnaissance Orbiter will attempt to image Atlas with the high-rise camera. That's the primary science goal. Get a high-resolution image of the nucleus. Measure its size directly. Look for surface features. HiRISE has a resolution of about 30 centimeters per pixel when imaging Mars from a few hundred kilometers up. Pointed at Atlas from 29 million kilometers away. The resolution drops to around 30 kilometers per pixel. That's enough to see the overall shape, enough to distinguish a roughly spherical nucleus from an elongated one, enough to measure whether Atlas is 5 kilometers across, or 10 or 15, but it's not enough to see surface details, not enough to resolve cracks or vents or any kind of structural features smaller than a few dozen kilometers. Still, is the best direct imaging we'll get before perihelion. Mars Express and the Trace Gas Orbiter will also observe with their instruments. Spectrometers, mostly. They'll measure the composition of the coma as Atlas passes nearby, looking for any unusual molecular signatures, and all three orbiters will track Atlas's position precisely. If there's any change in trajectory during the Mars encounter, if Atlas makes a course correction, or if Mars's gravity perturbs it in unexpected ways, the position data will catch it. What they won't catch, unless they're specifically looking for it, is a small secondary object. You'd need to do dedicated searches. You'd need to image the space around Atlas with long exposures, looking for faint moving points of light that don't match the background stars. You'd need to task radar if any of the Mars orbiters have suitable radar instruments, which I'm not sure they do, to sweep the approach corridor and look for unexpected returns. You'd need to coordinate all of this across multiple spacecraft and ground stations, pulling the data in real time and analysing it quickly enough to catch anything transient. As far as I know, that level of coordination isn't planned, which means October 3rd will come and go. HiRISE will get its images, the spectrometers will get their data, and we'll learn something about Atlas's size and composition. But if there's a secondary deployment, if something separates and heads toward Mars, we probably won't see it until someone reviews archived data months later and notices an anomaly. And by then, whatever has deployed would already be wherever it's going. Now, I want to be very clear about probabilities here. The chance that Atlas is technological and the chance that it deploys something at Mars are both low. Loeb himself would probably put the combined probability at well under 10%, maybe under 1%. This is not a prediction, this is a scenario analysis. But low probability doesn't mean zero probability. And when the stakes are this high, when the question is, are we alone in the universe? And is something artificial operating in our solar system? Even a 1% chance deserves attention. That's Loeb's whole argument in a nutshell. We don't need certainty to justify watching carefully. We just need enough uncertainty to make the cost of missing something unacceptable. And October 3rd is the first test of that principle. Here's a question that should keep you up at night. what happens if Atlas turns out to be technological? Not what would it mean for science, or how would it change our understanding of the universe? Those are philosophical questions for later. I'm asking something more immediate and practical. Who's in charge? Who decides what to do? What's the protocol? And the answer, as it turns out, is we have no idea. There's no international body responsible for responding to potential alien contact, no established chain of command, no decision-making framework, no plan. We have protocols for asteroid impacts. NASA's Planetary Defense Coordination Office tracks near Earth objects and coordinates responses if something threatening is detected. We have protocols for pandemics. The WHO has frameworks for international cooperation when diseases cross borders. We even have protocols for nuclear incidents. The IAEA monitors nuclear materials and coordinates responses to accidents or security breaches. But alien contact, nothing. SETI, the search for extraterrestrial intelligence, has some guidelines for what to do if we receive a radio signal from another civilization. They're mostly about verification, make sure it's real before announcing it, and consultation, talk to other scientists and governments before responding. But those guidelines assume we're detecting a signal from light years away, something that gives us years or decades to think about how to respond. They don't cover a physical object already in our solar system, moving at interstellar speeds, potentially making decisions on timescales of days or weeks. Loeb looked at this gap, this complete absence of preparedness, and decided someone needed to at least start the conversation about what a protocol should look like. He proposed something he calls the Lobe scale, a rating system from 0 to 10 for classifying interstellar objects based on how likely they are to be technological rather than natural. 0 would be an object that's obviously natural. It has all the characteristics of a normal comet or asteroid: typical composition, predictable trajectory, behavior that matches gravitational and outgassing models perfectly, nothing unusual. File it under interesting but explained. 10 would be an object that's obviously technological. It maneuvers in ways that can't be explained by natural forces. It transmits signals. It has artificial structures visible in imaging. It releases heat that doesn't match solar illumination, suggesting an internal power source. It does something that screams intelligence, that leaves no room for doubt. Everything in between is a gradient. An object with 1 or 2 minor anomalies might rate a 2 or 3, worth noting, worth watching, but not alarming. Something with multiple statistical improbabilities stacking up unusual trajectory, unexpected composition. Timing that seems too convenient might rate a 5 or 6. Ambiguous, could be natural, could be artificial, needs serious investigation. Atlas, based on everything we've discussed so far, probably falls somewhere in that 5 to 6 range. Maybe 7 if you weight the orbital mechanics heavily, not definitely technological, not obviously natural. Somewhere in the grey zone where you can't be certain either way and the data could support multiple interpretations. And Loeb's proposal is that any object rating above 5 on this scale should trigger an international response. Not panic, not military mobilization. A coordinated scientific effort. Every available telescope gets tasked. Every spacecraft in the vicinity gets redirected if possible. Data gets pooled internationally, because, and this is the key point Loeb keeps making, aliens don't care about our borders. They don't care which nation discovered the object or which government has jurisdiction. An interstellar visitor is a problem for humanity as a whole, and the response should reflect that. He goes further. He says there should be an organisation, a standing international body specifically responsible for monitoring interstellar objects and coordinating responses. Call it the Interstellar Object Assessment Office, or the Anomalous Visitor Response Team. The name doesn't matter. What matters is having infrastructure in place before we need it. Because right now, if Atlas makes a manoeuvre on October 29th, If it captures into orbit and we confirm it's technological, the response will be chaos. Individual scientists will publish papers. Media will go into overdrive. Governments will scramble to figure out who's responsible for deciding what to do. Conspiracy theories will explode. And by the time anyone coordinates anything, weeks or months will have passed. Loeb's argument is that we can't afford that kind of delay. The window for observation is narrow. Interstellar objects move fast. If we waste time debating who's in charge and what the protocol should be, we'll miss the opportunity to study the object carefully and gather the data we need to understand what we're dealing with. So he wants the infrastructure in place now, before Atlas, before the next visitor, before we're in crisis mode. And predictably, this proposal has been met with a lot of resistance. Some scientists think it's premature. They say we don't need an international organisation for something that's almost certainly never going to happen. Interstellar objects are natural. The odds of detecting a technological one are vanishingly small. Why build bureaucracy for a non-problem others think it's dangerous? They worry that having an official body responsible for alien contact gives legitimacy to ideas that should remain on the fringe. It makes the whole field of "are we being visited" seem more credible than it deserves to be. And there's a political dimension too. Who would run this organisation? Which nation gets to host it? How do you ensure it's not dominated by a few powerful countries while smaller nations get excluded from decisions that affect all of humanity? These are real concerns, legitimate ones. But Loeb's counter-argument is simple. We prepare for low probability, high-impact events all the time. Asteroid impacts are rare, but we spend money tracking them and developing deflection technologies because the consequence of being unprepared is extinction level. Pandemics don't happen every year, but we maintain surveillance networks and response infrastructure because when they do happen, speed matters. Nuclear war is unlikely, hopefully, but we have treaties and monitoring systems because the cost of not having them would be catastrophic. Why should potential contact with extraterrestrial intelligence be different? The probability might be low, maybe very low, but the impact, positive or negative, would be the most significant event in human history. Getting it right matters. Being prepared matters. And waiting until we're in the middle of an encounter to figure out what the protocol should be is a recipe for disaster. Now let's talk about what that protocol might actually look like. Because Loeb has sketched out some ideas even if they're not official policy anywhere. Step 1, verification. Before you do anything else, make absolutely sure the anomaly is real and not measurement error or instrumental artifact. Get multiple independent observations, different telescopes, different teams, different analysis methods. Confirm that what you're seeing is actually there and not a glitch in the data. This is standard scientific practice, but it's especially important for extraordinary claims. You don't want to trigger an international response based on a false positive. Step 2, characterization. Gather as much data as possible. Trajectory, composition, size, shape, thermal emission, any kind of signal or communication, behavioral changes over time. Build a comprehensive profile of the object. Understand what it's doing, where it's going, what it might be capable of. This is where coordination becomes critical. You need multiple instruments observing from different angles, at different wavelengths, with different techniques. No single observatory can do this alone. Step 3, assessment. Use something like the Lobe scale to rate how likely the object is to be technological. Not a final judgment, just a working assessment based on current data. If it's clearly natural, you can relax, publish the science, learn what you can, and move on. If it's ambiguous or leaning toward technological, you escalate. Step 4, communication attempt. If there's a reasonable probability the object is artificial, you try to make contact. Transmit a signal, something simple. A mathematical sequence, maybe prime numbers. The digits of pi, something that screams, "This is intentional, not random noise." Point radio dishes at it. Send optical pulses. Try every communication method we have and see if there's any response. This is controversial. Some people think attempting communication is reckless if the object is hostile. You're just confirming your presence and technological capability. But Loeb argues the risk is minimal. If it's already in our solar system, it already knows we're here. Earth has been broadcasting radio waves into space for over a century. Anyone with sensitive enough receivers within 100 light years could have detected us already. Trying to communicate isn't giving away information. It's just confirming that we're aware of the visitor and we're interested in dialogue. Step 5. Defensive assessment. While you're trying to communicate, you also need to evaluate threat potential. Can the object maneuver in ways that would allow it to reach Earth quickly? Does it have kinetic energy that would make it dangerous even without weapons? Are there any signs of aggressive intent targeting behaviour? Weapons deployment? Anything that looks like preparation for an attack? This is where it gets uncomfortable because we don't have good options if the answer is yes, it's potentially hostile. Our most powerful weapons, nuclear missiles, wouldn't be very effective against a 20-kilometre object, even if we could hit it, which is doubtful given how fast it's moving. Blowing it up just creates thousands of smaller fragments still on collision course. We'd make the problem worse, not better. Loeb is pragmatic about this. He says our defensive options are essentially zero against an object like Atlas if it turns out to be hostile. We don't have the technology to deflect or destroy something that massive moving that fast. Our only real defense is deterrence through communication, convince the object, or whoever controls it, that we're not a threat, that there's more to be gained from peaceful interaction than from conflict. But deterrence only works if the other side is rational, and if they value the same things we do. If they're automated systems following pre-programmed instructions, or if their goals are fundamentally incompatible with our survival, communication might not help. This is the nightmare scenario Loeb occasionally references, not the Hollywood version where alien ships arrive and we have epic space battles. The version where something appears, makes a calculated decision based on parameters we don't understand, and we have no way to influence the outcome. No negotiation, no defense, just the universe operating on logic that doesn't include human preferences. Step 6. Public communication. At some point, probably earlier rather than later, you have to tell people what's happening. This is tricky. You don't want to cause panic, but you also can't hide the fact that something extraordinary is occurring, especially if it's visible in amateur telescopes and people are already asking questions. Loeb's view is that transparency is better than secrecy. Tell the public what you know, what you don't know, what you're doing to find out more. Give regular updates. Don't speculate beyond the data. Admit uncertainty when it exists. People can handle ambiguity if you're honest about it. What they can't handle is being lied to or kept in the dark while rumours and conspiracy theories fill the void. And step 7, international coordination. Throughout all of this, you need nations talking to each other, sharing data, coordinating observations, deciding collectively what the response should be if the object is confirmed technological. Because once you get to that point, once you're certain you're dealing with alien technology, the decisions that follow affect everyone. Do we try to intercept it? Do we send a spacecraft to get closer looks? Do we attempt to capture it if possible? Do we just observe from a distance and wait to see what it does? These can't be unilateral decisions. One nation acting alone could trigger consequences for the entire planet. Loeb uses the phrase planetary defense, but he means it in a broader sense than just deflecting asteroids. He means defense of human interests, collectively making sure we don't stumble into a situation where someone's individual choice creates catastrophic outcomes for everyone. Right now, We don't have the infrastructure for any of this. We don't have the coordination. We don't have the protocols. We barely have the conversation started about what protocols should exist. And that absence of preparedness is what drives Loeb to keep pushing this issue publicly, even when it makes his colleagues uncomfortable, even when it damages his reputation in some circles, because October 29th is coming. In less than 4 weeks, Atlas disappears behind the sun, and if it makes a maneuver, if it transitions from passing through to staying, we're going to need answers to these questions very quickly. Who decides what to do? Who coordinates the response? How do we communicate with something that might not think like us or value what we value? We should have figured this out decades ago. We should have protocols ready. We should have an international organisation with clear authority and established procedures. But we don't. And if Atlas is the moment when we need all of that, we're going to be improvising, making it up as we go, hoping we don't make mistakes that we can't undo. Let me tell you about what happens when you challenge scientific consensus. Not with bad data, not with sloppy methodology, but with a hypothesis that makes people uncomfortable, that threatens established narratives, that forces conversations nobody wants to have. You get destroyed. Not your arguments. You, personally, your credibility, your reputation, your standing in the community. And Avi Loeb knows this better than almost anyone, because he's been living it since 2017. That's when Oumuamua happened, the first confirmed interstellar visitor. A cigar-shaped object that tumbled through the inner solar system, showed unusual acceleration that couldn't be explained by normal outgassing, and then disappeared back into the void before we could get a really good look at it. Loeb looked at the acceleration data and proposed a hypothesis. What if Oumuamua wasn't accelerating from outgassing? What if it was being pushed by sunlight reflecting off a thin sail, a light sail, the kind we've theorized about for decades as a way to propel spacecraft using radiation pressure instead of fuel? He published a paper exploring this idea, not claiming it was definitely a light sail, just saying the data was consistent with one and we should consider the possibility. The response from the astronomical community was brutal. Critics called it irresponsible speculation. They said Loeb was jumping to conclusions without sufficient evidence. They accused him of chasing media attention, of damaging the credibility of legitimate SETI research, of being the Carl Sagan wannabe who cried alien one too many times. NASA's position was clear. Oumuamua was almost certainly a natural object, probably a comet with unusual composition that produced asymmetric outgassing we couldn't detect directly. Natural explanation. Case closed. Move on. And most of the scientific community agreed. Papers were published showing how various natural mechanisms could produce the observed acceleration. Outgassing from hidden vents, sublimation of pure nitrogen ice, fragmentation events that looked like thrust. Oumuamua got filed away as weird comet, interesting but explained, definitely not aliens. And Loeb got filed away as that guy who sees aliens everywhere. Now, 7 years later, here we are with Atlas, another interstellar visitor, another set of anomalies. And Loeb making the same argument we should at least consider the possibility that it's technological, and the response even more hostile than before. NASA's Tom Statler has been one of the most vocal critics. He's called Loeb's claims about Atlas absolute nonsense. He said the data clearly points to a natural comet and that proposing alien technology is bad science that misleads the public. Chris Lintott from Oxford has been similarly blunt. He argues that Loeb's pattern is clear. Take any mildly unusual interstellar object. Ignore the straightforward natural explanations, and immediately jump to, it might be aliens. It's not skepticism, Lintott says, it's sensationalism, and the frustration extends beyond just Loeb's hypotheses. The SETI community, the people who've dedicated their careers to searching for extraterrestrial intelligence, using radio telescopes and rigorous protocols, are particularly angry because they're trying to do careful, methodical science. They're listening for signals. They're analysing data. They're being extremely cautious about making claims because they know how easy it is for the whole field to be dismissed as pseudoscience. And then Loeb comes along with his high profile. He's a Harvard professor, former chair of the astronomy department, widely published, media savvy, and he's telling the world that every weird space rock might be an alien probe. From SETI's perspective, that's poison. It makes their work look less credible by association. It makes it easier for critics to say, see, these people will believe anything. They'll call a comet a spaceship if it gets them attention. Funding becomes harder. Serious scientists become more reluctant to enter the field. The whole enterprise suffers. So the pushback against Loeb isn't just about Atlas or Oumuamua. It's about protecting the credibility of a field that's already marginalised in mainstream astronomy. But here's where it gets interesting, and where I think the scientific community is missing something important. Loeb's response to all this criticism has been remarkably consistent. He doesn't back down. He doesn't soften his claims. He just keeps saying science should follow the data, not assumptions. If the data shows anomalies, we should investigate. We should consider all hypotheses that fit the observations, even the uncomfortable ones. And we shouldn't dismiss possibilities just because they seem unlikely, or because considering them makes us look bad. He uses this line in almost every interview. If we assume everything is natural, we'll interpret every observation through that lens, and we'll never find anything artificial even if it's right in front of us. That's not a crazy position. That's actually pretty reasonable scientific philosophy. The problem is how he applies it. Critics say Loeb has a hammer and everything looks like a nail. They say he's pre-committed to finding alien technology, so he interprets ambiguous data in ways that support that conclusion while downplaying or ignoring natural explanations. And there's some truth to that. When you read Loeb's papers and blog posts about Atlas, there's definitely a pattern. Every anomaly gets framed as evidence for the technological hypothesis. Every natural explanation gets qualified with, but it could also be language that leaves room for artificial origins. That's not neutral analysis. That's advocacy for a particular interpretation. But, and this is the part I find genuinely interesting, is that necessarily wrong science is supposed to be about testing hypotheses, not defending consensus. And if nobody is willing to seriously explore the technological hypothesis because it's uncomfortable or career damaging, then who's testing it? Loeb argues that mainstream astronomy has a bias problem, not a data problem. The data is ambiguous, but the interpretation is overwhelmingly skewed toward natural explanations because that's the safe career move. If you publish a paper saying Atlas is a comet with unusual chemistry, nobody blinks. It's interesting. It's publishable. It might even get you a few citations. If you publish a paper saying Atlas might be alien technology, you risk your reputation. You get accused of attention-seeking. You make it harder to get tenure, to get funding, to be taken seriously on future research. So the incentive structure pushes everyone toward conservative interpretations. And Loeb's point is, maybe that's fine for most science. But for the question, are we alone in the universe? Which is arguably one of the most profound questions humanity can ask, conservative bias might cause us to miss the answer, even if it's staring us in the face. Because here's the asymmetry he keeps highlighting. If you investigate Atlas thoroughly, consider the technological hypothesis seriously, and conclude it's natural, what have you lost? Some telescope time, some research effort, maybe a bit of credibility if you are too enthusiastic about the alien angle. But if you assume it's natural without investigating thoroughly, and you're wrong, you've missed first contact with an extraterrestrial intelligence. You failed at the one moment in human history when the universe handed us something extraordinary and we dismissed it because the hypothesis made us uncomfortable. That's an asymmetric risk profile. The cost of a false positive is minimal. The cost of a false negative is catastrophic. And yet the scientific community is overwhelmingly optimized to avoid false positives, to avoid claiming something is significant when it's not, rather than to avoid false negatives. Loeb thinks that's backwards for this particular question. Now, his critics have a response to this. They say if we take every ambiguous observation seriously as potential alien technology, we'll waste enormous amounts of resources chasing false leads. There are thousands of asteroids, hundreds of comets. We're going to find dozens or hundreds of interstellar visitors in the coming decades as survey telescopes improve. If we treat everyone that's slightly unusual as a potential alien probe, if we mobilize international responses and coordinate multi-telescope campaigns every time something doesn't fit the model perfectly, we'll be crying wolf constantly. And eventually, when something genuinely extraordinary appears, nobody will pay attention because we've exhausted our credibility on false alarms. That's a legitimate concern. That's why Loeb proposed the Lobe scale to have a systematic way of triaging observations and deciding which ones deserve extraordinary attention. But the establishment response to the Lobe scale proposal has been lukewarm at best. Most astronomers think it's unnecessary. They say we can already distinguish between interesting anomalies and probable artificial objects using existing scientific methods. We don't need a new rating system that formalizes speculation, and there's resistance to the framing. Calling it the Lobe scale implies ownership. It's his framework, his categories, his definitions of what constitutes evidence for technology. That kind of personal branding in science makes people uncomfortable. It feels like ego rather than collaborative knowledge building. Loeb's response is that someone has to start the conversation. Someone has to put a framework on the table, even if it's imperfect, even if it gets modified or rejected. Because right now we have nothing. And having an imperfect framework is better than having no framework when we're potentially dealing with the most important discovery in human history. But the personal dynamics here can't be ignored. Science is done by humans, and humans have egos, rivalries, territorial instincts. Loeb is a high-profile scientist. He's published over 1,000 papers. He's advised PhD students who've gone on to prominent careers. He's been chair of Harvard's astronomy department, chair of the board on physics and astronomy of the National Academies. He has institutional power and media access that most scientists don't have. And when someone with that kind of platform uses it to push hypotheses that the majority of the community thinks are wrong, it creates resentment. People start questioning motives. Is he really following the data, or is he chasing headlines? Is this about scientific truth or personal brand building? I've read interviews where colleagues speaking anonymously suggest Loeb knows the alien hypothesis is unlikely, but promotes it anyway because it gets attention. Book deals, media appearances, that's character assassination disguised as scientific critique. And it's impossible to refute because it's about internal motives rather than external evidence. Loeb says he's following the data and asking uncomfortable questions. Critics say he's seeking attention and damaging the field. And there's no objective way to prove who's right about his motivations. What we can evaluate is the science, the data, the arguments. And here's what I find genuinely difficult about this whole debate. Both sides have valid points. Loeb is right that we should be open to unconventional hypotheses when the data is ambiguous. He's right that bias toward natural explanations might cause us to miss artificial signatures. He's right that we need better protocols for evaluating interstellar visitors, but his critics are also right that extraordinary claims require extraordinary evidence. They're right that you can't just point at anomalies and say therefore aliens without ruling out natural alternatives. They're right that credibility matters and that too many false alarms undermine the field. The truth, as usual, is somewhere in the middle. Atlas is anomalous. The trajectory is unusual. The mass is high. The chemistry is weird. The timing is suspicious. All of that is factual. It's in the data. It's been observed and measured by multiple independent teams. But anomalous doesn't mean artificial. Unusual doesn't mean designed. And statistical improbability doesn't prove intent. Natural processes produce outliers. Rare events happen. Coincidences stack up sometimes. The question is, at what point does the accumulation of anomalies tip the balance from probably natural but weird to probably artificial, or at least worth investigating as if it might be? And that's not a question science can answer definitively. It's a judgment call, a threshold decision, and different people with different priors will draw the line in different places. Lobe draws it earlier than most. He looks at Atlas and says, "This is strange enough that we should treat it seriously as a potential artificial object." Most of the astronomy community draws it later. They look at Atlas and say, "This is strange but still within the range of natural variation. Comet, unusual one. Sure, but comet. Who's right we'll find out on October the 29th. Or maybe in late November when Atlas re-emerges. Or maybe never if the data stays ambiguous. But one thing is certain, the scientific community's response to Loeb's hypothesis tells us something important about how science handles ideas at the edge of respectability, and it's not always pretty. So here we are, October 2025, days away from moments that might change everything or confirm nothing. October 3rd, Mars flyby, high-rise images, the first real look at what Atlas actually is beneath all that gas and dust. October 29th, perihelion, the blackout, the moment when Atlas either continues on its way out of the solar system or makes a decision we'll only discover weeks later. Mid-November emergence, when we recalculate the trajectory and find out if anything changed during those 2 weeks when we couldn't see a thing. 3 dates, 3 opportunities for answers, or 3 moments that leave us with even more questions. I've spent the last few hours walking you through every anomaly, every statistical improbability, every reason Avi Loeb thinks we should be paying attention, the brightness that appeared too early, the 33 billion ton mass that doesn't quite fit, the trajectory aligned just a bit too perfectly, the timing that seems almost deliberate. Is Atlas an alien probe? Probably not. The most likely explanation is still that it's a comet, unusual one. Certainly, but ultimately natural. But probably not isn't the same as definitely not. And that gap, that space between what we think we know and what the data actually proves, is where Loeb has planted his flag. He's not saying believe in aliens. He's saying stay curious, watch carefully, don't dismiss possibilities just because they make you uncomfortable. Because the universe has surprised us before. Continental drift, black holes, quantum mechanics, dark energy. Every generation of scientists thinks they've got the big picture figured out, and every generation discovers something that shatters those assumptions. Maybe Atlas is just another weird comet. Maybe in December we'll all look back and laugh at how worked up we got over some statistical flukes and ambiguous chemistry. Or maybe, just maybe, we're living through the most important autumn in human history. The season when we stop being alone. When something from another star system decided our neighbourhood was worth a closer look. We won't know until we know. But we're about to find out. If this deep dive into the cosmic mystery kept you engaged, hit that like button, but only if you genuinely want more content like this. Subscribe if you're the kind of person who needs to know how this story ends, And drop a comment telling me what would you do if Atlas turns out to be technological. Would you want to make contact or stay hidden? I'm curious where your head's at on this. Now, turn off the lights, let the story settle. And remember, the universe is under no obligation to make sense to us. Sometimes it just is what it is. And sometimes it's stranger than we ever imagined. Sleep well, or try to. Anyway, October 29th is coming.